Welcome everybody to this session, this free session at sec4dev about the 101 of software security. So we're going to learn the basics of secure coding today. And we have about 3 hours. So after the talk, also feel free to ask questions. I'm going to be here and available if you have any questions regarding the talk. If we build houses the way we build software, then bricks would be falling on our heads all the time. Now, if something happens with software, something bad happens with software, such as there's a vulnerability and somebody exploits the vulnerability, this is not such a tangible thing as a brick falling on us. That's why I think in the construction world, everybody knows that we need to care for safety. We need to care about that the walls and the roofs and everything is stable. We know that we have to care about that because otherwise lives and our health are a danger. In software, it's basically the same problem. Our lives and our safety and our health can be a danger if software doesn't work properly or has security vulnerabilities that somebody exploits. But still, in most of the time, software vulnerabilities are so intangible that people don't seem to care so much. I live in Austria, and I've seen on TV recently that the construction sector in Austria has not grown in productivity since the 90s. So from the 90s until today, we're not able to build houses and buildings faster than 30 years ago. We are still at the same pace. But what has changed a lot is that there are a lot of laws that mandate that we build houses and we construct houses in a safe and secure way. So there are lots of laws out there that these companies need to comply with. And that's why the speed hasn't increased. But in the software world, everybody is able to, it feels like everybody can just watch a YouTube video and then be a professional in software development, which is not the case. So building secure and good and robust and maintainable and reliable software is very hard to do. But our thinking still mandates that we should build software quickly. It needs to be in the market today. And that's a requirement that's detrimental to security. So security and quality and reliability of software nowadays is not high because of that push. We need to get out fast. And then if I read those newspaper articles, like there was one recently, I think it was in the Washington Post or New York Times, where a few people just rebuilt software that was built by the state. I think it was about COVID-19 vaccines or something like that, that cost a few $100,000. They built it in an hour or so, and it cost $500. This makes me a bit sad if I read this, because I'm pretty sure that this software does not hold up to software security standards that it's supposed to hold up to, because it's about health data, right? So if you read newspaper articles that there was a software by the government that cost $1 million and somebody built it for $50, I'm pretty sure the quality of that piece of software is not as good as it should be, right? So be careful when you read this. So that's the reason why we're here. There are lots of data breaches, there's bad software, there's vulnerabilities, there's hacks, there's data breaches, and we want to avoid them. I'm just going to present myself first. I'm Tom. I work for a company called SBA Research. We are a research center for information security located in Vienna, Austria. And the company is basically two parts. There's a applied information security research part. That's the bigger one, about 2/3 or 70-something% of people work in the research area. And there's the professional services area where we do consulting. And this is where I work at. I'm in the software security team of SBA Research. Now, I started out as a penetration tester. So I test software systems for vulnerabilities and try to exploit them, and then try to make recommendations about how to make those systems more secure. So that's my main job, or yeah, it's still one of my main jobs. But I'm also now changing a bit towards secure software development lifecycle consulting. So I work with companies in improving their secure development lifecycle. I'm also a software developer myself, and I love software development. My heart beats, or at least a part of my heart beats for software development, and especially for security architecture in software. I personally specialize in application security, so web apps and mobile apps, smartphone apps, and apart from that, secure development lifecycle, automation, education. Speaking of education, I'm also a security trainer, so I train software developers on software security. And that was also one motivation to found the sec4dev conference and bootcamp. I'm one of the founders. And now you all are part of the sec4dev family, so welcome. I'm happy that so many people are interested in this. So just a short view on the agenda for today. We will see why we need software security and why this is a problem that it's not there as much as we want to. Then we're going to have a look at some specific coding practices that will help you against a wide variety of security problems, right? It's something that you should internalize as a software developer so that you can write more secure software. We will also look at clean code. Now, this sounds like it doesn't relate to security so much, but you will see that it does. And we will see why it relates to software security. And then we will widen our view and we will look at the secure software development process. So not just the coding part, but also things like education, requirements analysis, threat analysis, automation. We will look at different tool types of automation, what is out there, what are their strengths and weaknesses. So to get you a bigger picture. And we will talk about one specific standard that can help you also get that bigger picture for your development process. I will pick out, at this point 5 here, one specific part of the development process that is dependency management. Most pieces of software out there running code is composed of usually more than half of it's foreign code. So it's libraries and frameworks and runtimes and containers and everything that you pull in, and there's this little piece of software that you wrote running on top. So not just the code you write is important, but also everything around it. So we will have a look at how we can manage security of dependencies like libraries and frameworks. And then we'll look at some lists of common security vulnerabilities, some of those top lists out there, and we will have a look at how they're composed and what's in there. We're not going to go super deep into each one of those vulnerabilities, but I want you to have an overview and I want you to know where to get more information. Speaking of where to get more information, I have also composed a short list of some learning resources that I personally found awesome and where I learned a lot about software security as well. And there are going to be some book recommendations also throughout the talk. So this is our agenda for the next 3 hours. There's probably going to be a break somewhere in the middle. Let's see where exactly that is topic-wise, but I think at around 10:30, 10:45, I'm just going to make a short break of maybe 5 minutes or 10 and open a window and let some air into our brains, and then we get back to secure coding. So just that it's going to be rather spontaneous. I can tell you an exact time right now. You folks have sent me a lot of questions beforehand. There was, I counted, it was 64 questions. That's 2 to the power of 6. I love the number. I'm very happy that's 64 exactly. That's just my nerd. That's my nerd me. If you have any additional questions, then please ask them on Slido. Here's the links. Go to Slido.do or scan the QR code. If any questions arise during the talk, this is where you can ask them. There's going to be a little pop-up where you can choose the room that you're in. And there you have to choose Software Security 101, Secure Coding Basics, that the questions go into the right place because there are many parallel sessions running right now. So there's bootcamps also running specifically. Great. So I hope I can answer most or some of those questions you asked me beforehand, probably not all of them. But if you have any additional questions, please ask them here. Software security is a complex world, and you're not going to get software security for free. Unfortunately, it's not going to be like you can do it, you can learn it in a day or two. It takes a long time to have an overview of that world. Now, what I want to do today with you is to navigate through that landscape and show you all the mountains and rivers and woods that are there and what they are good and not so good at, to give you just an overview and so that you can navigate through that world yourself. There will be places where you have to get into the specifics of the topic here and there. Of course, we cannot go from 0 to 100 in 3 hours, but I want you to have an overview over that landscape. Cool. So why are we here? Now, why do we want to have software security? Isn't it enough that the software we create is just running and working? Isn't that enough? Well, most of the time, it's not. There might be some customer expectation that there's no data breach when you write software for customers. There might be some expectations of your organizations towards you that you write software in a secure and reliable way. It might be compliance regulations. So there might be a law out there that is important for you. Like, for example, the data protection laws are probably important for almost everybody because everybody's processing personally identifiable information, PII. Then GDPR might be a matter. Or if you are, I don't know, if you process credit card data, it might be PCI DSS, Payment Card Industry Data Security Standard. That's something that's relevant for banks and so on. There's stuff that is relevant for the automotive industry and so on and so forth. So there might be laws that mandate some security controls in your software. There is hopefully some sort of intrinsic motivation. I think there is, because otherwise you wouldn't be here. And maybe some engineering ethics that you want to write robust and secure and maintainable software. There might also be something like an imposed security posture. Now, what does that mean? Let's take as an example. Some of you might have the Signal chat app, the instant messenger, installed. Now they have an imposed security posture of end-to-end encryption and privacy by design. That's what they say about themselves. So they implemented end-to-end encryption for their messages, not because of a compliance law that mandated them to do so. The GDPR doesn't say you have to end-to-end encrypt it all, but they want their app to have this security posture and say, we are a very secure messenger, we valued privacy, and so on. So there might be something intrinsic that you want to push out to the customers, right? Software is everywhere. So every company basically out there, or most companies, are software companies. Some realize that they are, some don't realize that they are. Almost all organizations out there are running software in one way or the other. Many of them are even creating software on their own. And those software products that are running everywhere are more and more interconnected, and that opens a myriad of attack vectors that we need to think about and that we need to take care about. Now, I think, and I'm not the only one who thinks that healthy growth as a software company, and you probably are a software company, is only possible if you think about software security from the start. Now, if you get back to the construction example, think if we build houses the way we build software, bricks would fall on our heads. Now, imagine your boss tells you, we need to construct that building in 3 days. Go, okay? And he gives you a bunch of bricks and cement. And then you start putting one brick above the other. You don't think about the design or the stability of the walls and roof and everything. You just start building, like you build software, right? You don't think about it, we just build it. And then after 3 days, there's something that looks like a house, and it's not. It's standing there. It's not breaking down. And then somebody tells you, the security guy, right? This wall is not going to be stable. So if there's strong winds, that wall is going to break down. And that's like finding a design problem or architecture problem in software 3 years after. And then imagine you want to change that wall. You want to put out the wall and put in a new one after the building has been constructed. That's the equivalent in software when you want to change the architecture and design when the software is already it's already implemented, it's already running, people are working on it, and so on. So the later you recognize that there's a security problem in terms of architecture and design, or maybe also bugs, the later you notice, the more expensive it's going to get. So if your boss tells you security is not something that we can afford, so we have to leave it out or we have to do it later, you can tell them and tell them I told you. We need to think about it from the start, also from an economic perspective. It's gonna be more expensive in the end if we don't think of it from the start. It's gonna be more expensive in the long run. Or put the other way, weeks of coding can save you hours of planning, right? And again, you see that building constructed in the background. That's technical debt. What I just explained is called technical debt. So it would take a lot of resources and money and time by a lot of people to make that building something stable and robust, right, in the aftermath, so when it's already there. Great. And so with all those activities and with everything, with thinking about security from the start, we are trading initial velocity for sustained velocity. So if you want to be quick at the beginning at all costs, it's gonna fall back on you later. And there's a really good book I recommend. I think you can even download it for free by now. Just Google it. It's called Building Secure and Reliable Systems. I think it was written by a bunch of Google engineers, or at least somebody of Google was involved there, I believe. And they have a chapter that's called Initial Velocity versus Sustained Velocity. And that's exactly the whole point. If you want to be really, really quick in the beginning, it's going to be at the cost of sustained velocity, right? So just pushing out stuff without thinking about the architecture and security and design and reliability at the beginning, just pushing it out as fast as possible, and then taking that prototype to make the real product is gonna cost you sustained velocity. So you're gonna be slower in the long term. So stop the short-term thinking and start thinking long-term, right? And introduce security at the beginning when you start with the product, and throw away that prototype. People take prototypes and make them a product. That's not the way it goes. You can start over. When you know that prototype is working, throw it away, archive the Git repository, and then start over. We will add security later, just no one does it, or it's very cumbersome and very, very time and money consuming in the long run. So this is a great book recommendation, and you can find it, I believe it's even free. Now, we're going to talk a lot about flaws and bugs in this presentation. So I just want you to know what's the difference between those two things. On the picture, you can see the Tacoma Narrows Bridge. That's a bridge that was, I think, built in the 40s in Washington State in the US. Washington State, that's northwest. I think Seattle is the capital. Somewhere in that state, there was this bridge. And when there were strong winds, the bridge started shaking, and eventually it shook it so much that it broke down. Now, what happened there was not a bug. A bug would have been, for example, somebody forgot to put a screw at a certain place, and the bridge broke at that part, and then everything else broke apart. That would have been a bug, but it wasn't. Everybody who was involved in constructing the bridge constructed it exactly the way that designers and architects supposed that it would look like. So technically, it was soundly built, but the error was in the architecture. So it just didn't have enough pillars and ropes and everything to make it stable enough for winds from 60 kilometers per hour upwards. That's a flaw, right? So an error, a mistake that happens in the design and architecture phase where you design the overall system is called a flaw. Something that's an implementation error, for example, a line of code is wrong or a security check is missing in a small part of the code, that's a bug. Design architecture, threat modeling, flaws. Implementation error, bugs. And there is a special case of security bugs that is security bugs. Great, so let's talk about the core security concepts that we're always talking about when we talk about flaws and we talk about security bugs. There are basically 3 core security concepts, and I want to explain them quickly. Confidentiality is when you don't want anybody else to read the data. So you don't want the data to be disclosed to anybody who is not supposed to see the data. That's confidentiality. That's the C in the CIA triad. There's also integrity. So we don't want anybody to first see the data, but also not modify the state in the system or the data in there. So if anybody is able to modify data in the system without them having privileges to do so, that's an integrity breach then. And availability is also an important factor. We don't just want the data in there to be not readable to anybody, not modifiable to anybody, but we want the system to be available. That's also a security concern. That looks like it's a bit apart from the rest, but security is also about, the system being available and running. So if somebody is able to attack the system via a denial of service attack, so send so many requests to the server until it goes down, that's a security problem as well, not just reading confidential data out of the system. So these three terms are the core security concepts, and they are called the CIA triad that you can see here on the right. There are some other concepts just for you to know the difference. Authentication is when I, as a user, have to prove against the system that I am the owner of this account. So that's usually done with username, password, or multi-factor authentication. That's authentication. And once I'm inside the system, there might be a role that I have a user in the system, and that role I can use to, for example, see the administrative part of an application. That's authorization. So authorization happens when I'm already authenticated. So I logged in already, and I might see some parts of the application I might not see. So the Hopin platform, for example, I have permissions to go backstage and to stand here on the stage. So I can click that link and I'm authorized to see that part of the application. That's authorization. But before that, I had to log in with my Hopin account, and that's authentication. Accountability is also an important term. So say, for example, you have a system where we have medical data in there, in a hospital or anything, and you are authorized to read data because you have a patient and you have to take care about them. Now, even though you're authorized to see the data of all those patients, it might not be authorized, technically authorized. It might not be advisable to read the data of everybody because you might not be treating each and every patient. So what those systems usually have is some sort of accountability. That means they log if you as a person have looked at a record of a certain patient, so that afterwards you can have a look at, are people or employees at a hospital maybe misusing their privileges to see medical data, right? That's you have to be able to be held accountable for what you do with and in the system. Great. So these are the core security concepts. We have some design security concepts. Again, these are, we're talking about flaws here and not bugs, potentially. I want to go over, I think it's a list of about 10 design security concepts, and I want you to understand what they are all about. We'll start with least privilege. Least privilege means that you want a person or a process of your software on an operating system to run at minimal privileges. Why do you want that? Because if something happens, if a vulnerability is exploited, or if something bad happens to the system, that the damage potential is just as low as possible, right? One very common example is that people should not have administrative privileges on their computers, on their laptops. I, for example, I have two separate accounts. I have one normal user account and I have a separate admin account for that. So even if a software is running, malicious software is running on my computer, at least it cannot run with administrative privileges. Now, the argument sometimes is that, the company doesn't trust me. They want to put away rights from my user account. But we need to change that thinking a little bit, because it might happen that there's malware on my computer because of a vulnerability exploited. And if that happens, you don't want that malware to have access to all your documents and maybe to install software and everything. So if you reduce the rights of people on a computer, that's called least privilege. Also, if you run a web server on an operating system and you run it with a non-administrative user, if something happens to the web server and it's exploited, at least it cannot so easily distribute itself throughout your network. That's least privilege. Separation of duties is a little bit different. It relates to least privilege, but it's not the same thing. Imagine, for example, you're a company where lots of money are transferred back and forth, and for the matter, if, for example, there's a transfer of money of more than, say, 10,000 euros, then there needs to be a second person who confirms the transaction. if that is the case, that's an example of separation of duties. So there need to be more than one person to authorize high privilege transactions. That's separation of duties. It is a form of least privilege because each person has just a narrowed down set of privileges, but it means that it needs multiple people to do a high profile transaction. That's separation of duties. Defense in depth means that I don't just have one security layer and that's it. So a negative example of defense in depth would be you have your company network and you have your firewalls, but once a piece of malware is running inside your network, it has access to everything. There is no separation. There's no network separation, for example. Each client has access to all the clients on the network layer. It has access to all the servers and everything. That would be a missing defense in depth. There's just one fence. If that fence breaks, then the attacker is inside your network. Now, a positive example of defense in depth would be that I have split the company in different network areas, maybe a high privileged network area where the servers are, maybe a lower privileged, maybe a guest network where guests can log in and use the internet but not access any of your servers. That's an example of defense in depth. Also, a good example of defense in depth, maybe some of you have heard of it, is a content security policy that's used in web browsers to protect against so-called cross-site scripting attacks. We'll talk about that later. If you have solid cross-site scripting protection in your application plus a content security policy, that's defense in depth or layered defense. It's also a name for it. If you work in the safety area, you might be not just concerned with security, but also safety. Some parts of those two words are contradictory. Some are not. What are examples of fail secure versus fail safe? Fail secure would mean that if the system is breached or if a mistake or error happens, that it's going to shut down so that nobody can read maybe data that's in there. Fail safe would mean it opens up. Let's take an example of a door. So say we're in a server room here and we have electronic door locks where people can authenticate with a smart card and go in. Now, if the electricity goes down, we don't have any electricity anymore in a room. What happens when you have fail secure? It would mean that the door closes. No one can get in. It's closed by default, and only it can be opened with your smart card. So default close would be fail secure. But on the other hand, that's not safe. So it's not if you go about saving people's lives and their health, you would rather open up the door, because if there's a fire in that room, for example, and electricity goes down and the door is locked, people cannot get out, right? That's an example of fail secure versus fail safe. That's my favorite design security concept. It's called economy of mechanisms. It's also referred to as keep it easy and keep it simple, right? The KISS principle. The more complex systems are, the harder it is to assess the security of them. So make sure to keep stuff as simple as possible. The more complex software systems get, the harder it is to somebody to assess its security. So keeping stuff simple is a very positive thing for security, usually. The principle of complete mediation means access control at every request, especially, for example, if you have a web application that talks to a server via an API, then it's important to do the access control at every single request, right? Because we're in a stateless world. There's no connection between one request and the other. You always have to suppose that an attacker can send every request at every time to the API. Complete mediation means access control at every request. Open design means, for example, if you design software or you design a cryptographic algorithm, that it's usually advisable to open up the design. So just because you take your piece of software and put it on GitHub, it shouldn't be insecure, right? You might think that people could look for vulnerabilities in there, but in an ideal world, that's not the case. In an ideal world, everything that's secret to your instance of the software is kept maybe in environment variables, in the configuration, in secrets, but it's not part of the code. So the code itself, even though you publish it, the software should not be insecure. So even if, say, Microsoft published the source code of their Windows kernel, it shouldn't, in an ideal world, it shouldn't be more insecure than the other way. Least common mechanisms means that if you have, for example, you have an application that has a part for end users and a part for administrators, you should separate those two things, and you should run them on different systems, right? So that if that public part is breached, that the other part is not breached with it. You will see that some of those core design concepts are contradictory. So you can never make all of them work 100%. It's always going to be a trade-off between two things. You will see an example soon. A very important part in security is also psychological acceptability. So say there's this security guy that's new and over motivated to secure everything, right? There's this bad cop security guy, and they say this needs to be shut off and this needs to be turned off, and he's always the person that says that's a no-sayer, right? The naysayer who says we don't, or we need to have stronger authentication. We need multi-factor authentication with 6 factors, all those things. Now, if you do that, and if you exaggerate these activities, it means that people will not accept those security measures, right? So if you have security measures, people need to accept them. Otherwise, they're going to think about how to circumvent the security measures if they're negative for their daily work. If they cannot get their daily work done because of security measures, you're always going to be the bad person. You're always going to be the bad cop who says no, and we need it stronger, and we need it shut down, and so on and so forth. So for security folks, it's very important to have this balance between security measures and the usability. So psychological acceptability means usability of security measures. Weakest link is an idea that says that if you have several security measures in a row that protect a certain resource, that the attackers are always going to look for the weakest link. So they're always going to look for the weakest protection to get inside. So make sure to always focus on the weakest link of your security protection chain. Now there's I think it's the last one, leveraging existing components. That means that security critical parts of your code, you should not reinvent the wheel all the time. So for example, an authentication system, there are many ready-made libraries and frameworks out there, identity provider software, and so on. So don't reinvent the wheel on security critical things, because there might be already well-tested and reliable software that you can go and use, right? None of these design security concepts are absolute. So none of these is going to say you have to have the least privilege, the least possible. It's always going to be a trade-off. These design principles are they just should tell you or should give you some perspective or some dimensions that software can have. And you're going to have maybe less separation of duties, but more defense in depth, whatever it is. Just some principles that might help you have a different look at your design and architecture. Great. So if you're just getting started and you want to say, okay, I want to choose a programming language that is good for security, I'll tell you a secret. So there are some languages that protect against certain vulnerability classes by design, but secure software can be written in any language. There isn't that one language that's the best in security. It's like, people make a religion out of everything. If you ask somebody, what's the best operating system, you have to tell them it depends on what you're going to do. And it's the same for programming languages. There are programming languages that are better for certain cases and others that are worse for those cases. Secure software can be written in any of those. It's important that you master the language and the security features of those languages in order to be able to write secure software, but it doesn't mean programming language X is bad for security. That never holds true in the long run, right? But everybody knows some programming languages out there that have much low quality code around and so on. Why is that the case? There are some languages where you see more low quality code. That's because some languages have low entry barriers and people can start writing and publishing software even though they don't have so much experience in development. And that's why you see some specific languages, you see bad code out there, right? That doesn't mean that language is bad. It just means that the entry barrier is lower and people can start publishing earlier. But we need languages with low entry barriers so that people can get into software development and start learning and learn development. And that's only possible, or that's probably possible better, it works better with languages that are easier to understand, right? So there's nothing wrong with writing software in PHP or JavaScript. You know, those are two languages that have kind of a bad reputation, and I don't think it's justifiable, but they have a bad reputation. But I think most of these discussions that it's just a bad language by design is basically bullshit. Still, I'm going to tell you some criteria for choosing a language that have a security impact. And we're going to talk about these 5, although parallelization is something, sorry, that's an advanced topic. I'm not going to dive deep into this one, but the others are important for security. Let's start with the very basic and low-level one. It's called memory safety. So what does it mean when a language has memory safety? Now, some programming languages have so-called pointer arithmetics. So it means that you have a variable like this p here, and you can assign it another variable. And that variable now points to a certain spot in your random access memory, in your RAM, in your memory. And you can directly change where that pointer goes to. So you can increase it so that it's the next place in memory. You can decrease it and so on. Some languages allow that low-level changing of pointers and pointer arithmetics, and other languages do not. There's also things like, you know, memory safety has many flavors. It's also array bounds checks. So if you have an array that has 3 objects in it, some languages check if when you're accessing the 4th object that doesn't exist, it's going to throw an exception. Others don't. It just gives you the next object after that array. There's also null pointers in some languages, like Java, for example. And some languages allow accessing unallocated, deallocated, or uninitialized memory, and other languages do not, and going to throw an exception. So if a language does not have memory safety, that means that less checks have to be done at runtime. And that means that these languages are faster. So languages, low-level languages like C and C++ are 2 very popular examples that only have some very specific aspects of memory management. They are usually faster than other languages. So scripting languages like Python who have memory management, they're going to be slower for that purpose. So why should we bother about that when it comes to choosing a language for security? Well, non-memory safe languages, like those fast, low-level languages, are susceptible to some vulnerability classes by design, like, for example, buffer overflows being the most common example here. Buffer overflows allow an attacker to gain control over the execution flow. So they can take an input, input it into the software, and they're going to probably, if there's a buffer overflow vulnerability in it, they're going to overwrite parts of the memory and they can take control of the program flow, right? That's a very bad vulnerability if it happens. And just to give you some examples of which languages do have memory safety and which ones do not, C and C++, machine code, assembly, and so on, they do not have any memory safety. You are totally responsible for securely managing those pointers and securely using functions like string copy, mem copy, and so on. There are other languages that have, it says here, some form of memory safety. In detail, those languages in their memory management differs. So it's not the same everywhere. But those languages basically have memory management of some sort. So you don't have to care about pointers and you don't have to care about buffer overflows usually in those languages. There might be some very small edge cases in some of those, but basically you're protected against this class of vulnerabilities. there are two new kids on the block, that is Rust and Go. It's two languages that try to settle somewhere between the Java, C# world and C++ in terms of speed. So they're very fast executables, but they come with a basic memory management. So the attempt to sort out that memory management problem. It says mostly here because with both languages, you can go into the unsafe world. So there's unsafe keyword where you can have pointer arithmetics again. But the good part is that probably if you don't, have a bad design of your software, 99% of your code are going to be memory safe. And there might be some small, very specific parts of your code where you don't have memory safety, but you really need to know what you're doing if you use those unsafe worlds of those two languages. But you will have memory safety, mostly. Yeah. Then there's another concept called type safety. So what is type safety? Type safety is, for example, this variable holds an integer. And if you tell a type-safe language that this variable holds an integer, it is guaranteed to hold an integer. Or this array has 10 elements. If you have a type-safe language, it's guaranteed at runtime that this array actually has exactly 10 elements. Type checking can happen both at compile time or at runtime, depends on the language. And type safety means that those assertions that this variable is a number, that this is guaranteed at runtime and cannot change at runtime. Here's an example of a non-type safe language, namely PHP, but be aware that PHP is going towards type safety with newer versions, so you can have types optionally if you want to. A non-type safe example would be, I'm assigning a string here with 2 characters 4 and 2 to the variable a, and this is now a string. Now, if I add 42 to that string, it converts to an integer. So at runtime, there's no guarantee that it's always going to say a string. It's always going to stay a string. I did not declare that it should be a string. It was implicitly declared by assigning a value to the variable. So in PHP, at least if you don't use those newer language features for type safety, is non-type safe. Also, non-type safe is JavaScript. Here are some really funny examples of how you can juggle with those types, and you can subtract and add numbers to strings, and there are sometimes weird results and so on. So JavaScript is also a non-type safe language. Again, the question, why should we care about type safety and security? Well, type safety or type safe languages have long-term advantages. First and foremost, they have better IDE support. So if you write software with a language that has type safety in some form, you're going to get better suggestions by your IDE because it can very well see which types can be returned in this function or which functions can be called from there, or and so on and so forth. So the less flexible the language is at runtime, the better the suggestions by your IDE and the more it's going to help you. But this is not yet so much security related, but if you look at security automation, there's one tool class, we're going to look at that later, it's called SAST, so it's Static Application Security Testing. And these tools have, they can find the path through your code better if you have a type-safe language, because it's more predictable how the program is going to behave at runtime. So you tend to have less false positives when you use automation with type-safe languages. And in general, you have less unexpected errors. So some vulnerabilities, I'm thinking about one, I think WordPress had one recently where you could read or edit an article because of such a type juggling thing where a string was confused with an integer. And so everybody could edit WordPress articles even though they didn't have permissions. I think that was the vulnerability. It was because of non-type safety of the language. So let's have a look at certain programming languages that have and do not have type safety. Might be surprising to some of you folks that TypeScript doesn't really have type safety, because type safety means that at runtime, so when the software is running, it guarantees that a variable is of a certain type. TypeScript is not, it's not the case in TypeScript. It's only going to give you that when you look at the code, and the IDE is going to be able to predict things. But if at runtime you assign a number to a string, it's going to work. There's no exception thrown. TypeScript is a superset of JavaScript, so it extends JavaScript with some features. JavaScript, very popular language in web browsers, is also a non-type safe language. PHP is also a non-type safe language, but it is moving towards type safety. So there are some features in newer versions of PHP where you can use type safety if you want to. Python is also not type safe. There are some languages with some form of type safety. Again, it differs in the details, but Java is a classic type safe language, C#, Rust, Go, and so on. So here you can see an overview of type safety in different programming languages. Parallelization support could be a factor if you if you're running software where stuff needs to be processed in parallel. So when parallel computing and high speed and distributed computing is something that's important for you, then it might be advisable to choose certain languages that are designed for robust parallel computing. For example, Elixir, Erlang, Haskell, Rust, Clojure. So these languages are designed for this. And others have less focus on parallelization, right? So I'm not going to dive very deep into this because it's not so directly, and it's not a basic topic, it's an advanced topic, but just so that you know that some languages are made for this and others are not. Right, so Sandbox support. Now, if you write software, you should expect vulnerabilities, and you should expect attacks to happen. And if you expect attacks to happen, attack surface reduction is a key to a sound security architecture. Attack surface reduction means making the software run in an environment where even if a breach happens, even if an attack happens, that the attacker cannot do so much with that process that they just exploited, right? So when you put a process into a sandbox, you need to lock you lock it down to only the necessary capabilities. So that process, that software can only open certain ports, can only talk to certain other servers, can only read and write to certain directories, and so on. It's also a form of least privilege, right? And there are different sandbox technologies that can help you put processes into a sandbox where the dangers are not so big. So if you see that beach here on the right-hand side, and you would put a baby on that beach, there's a lot that can happen around, right? So there's the water where the child could drown. There's trees where the child could hurt itself. There are other kids that could not treat the baby well, and so on. So if you put the baby there, it's not in a sandbox, and there are lots of dangers around it, right? So the sandbox would be something. There are sandbox technologies on different levels. It's something that locks down the process to only to certain features that it can use. On the operating system levels, there are different software products like AppArmor. It's very popular in Ubuntu Linux distribution. There's SE Linux. That's created by the NSA, by the way. There's seccomp, where you can use in Linux to lock down a process. There's changeroot to lock down file systems, so what the process can see in terms of files around it. That's operating system level. That's things that you can use there. On the platform level, there is your web browser. Your web browser locks down your JavaScript code to only that origin where it is running on. So JavaScript code cannot access your files on your file system and your documents that are on your desktop, for example, unless you open a file and upload it to the web application. Then JavaScript code can handle this file, but not by default. So running in the background, it cannot access your file. That's sandboxing, basically. You sandbox your JavaScript process in a web browser. And on the language level, there are also possibilities. Two examples: .NET Code Access Security is something you can use in .NET, and the Java Security Manager is for the Java language, and you can lock down the Java process to only certain features. That child process here on the right is attempting a sandbox escape, and I think it will be successful. There's a talk that is related to sandboxing technology. It's by Alexander Relsen, who was also a speaker at the first sec4dev 2 years ago. He will talk about seccomp for developers, exactly what I mentioned before. It's a Linux operating system feature that you can use to lock down a process to only a few things it can do. So even though that software might get hacked, the attacker sits in a small sandbox and cannot move back and forward. He's a great speaker, and he did, I think it was the last talk at the first sec4dev 2 years ago. Here's a link to the description of the talk, so if you want to have a closer look at what he's going to be talking about. Also very important is the availability of secure frameworks. So don't reinvent the wheel. Build on proven technology if possible. There's going to be things that are repetitive that you will have to implement over and over again, like authentication, like authorization, like session management, like maybe some cryptographic operations, and so on. So like configuration, you need to read something out of a configuration file. If you do that, you on your own over and over again, it's more prone to errors as opposed to when you use something that's already there and already done. Frameworks usually give you that type of functionality for your software. Make sure to choose your framework wisely and have a look at what they do about security and their documentation on security. Is there something, do they mention security in their documentation or not? Do they have a security contact if somebody finds a vulnerability and so on? These are factors that you can use to assess whether or not they care about security or not. Don't be tempted to just pull in everything and every library that's out there for all the cases, because then you're gonna increase the attack surface again. So only pull in what's strictly needed and pull in where you're convinced of the quality of the software. If there hasn't been a commit in the GitHub repository for the last 12 years, it's probably not something you want, right? It's not maintained. So typical jobs I already mentioned. Some of those is authentication is usually done by frameworks. Session management is usually done by frameworks. Authorization, persistence layers, templating for HTML, configuration, and so on. So you don't want to reinvent the wheel over and over again, but at the same time, you don't just want to pull in everything. So try to find a middle ground on these things. Here are just a few examples of good web frameworks. So as I told you in the beginning, I'm a web security person, so I can tell you good frameworks in the web world. It's in JavaScript, Express.js is a server-side framework for the web application server. And there are some front-end frameworks or single-page application frameworks, how they are called, Angular, React, and Vue.js. In terms of security, Angular is the better one of those three. We will see later why that is the case. Java has one very popular framework that's Spring framework. PHP has two very popular ones. One is Symfony, and the other one is Laravel. And they are even borrowing parts of the code from each other. So they don't hate each other, and they are pretty similar in some functionality. Ruby, there's Ruby on Rails, has been around for a long time. And C#, there's .NET Core, also a very solid new web framework. So these are frameworks that are solid, that have been around for some time, and yeah. So to sum this up, this part of the talk, security criteria for choosing a language. There's the concept of memory safety. So whether or not the programming language manages the memory for you and protects you automatically against vulnerabilities like buffer overflows. There are some languages like C and C++ that do not, at least in most part, protect you against this class of vulnerabilities. There are other languages like Java, C#, and Go and Rust that do protect at least 99% against this vulnerability. There's also type safety. It's rather indirectly related to security. So basically, you can write secure software in every programming language, but some tools like static application security testing will have an easier life if you have a type-safe language. Parallelization support is something that you should look into if you have to do parallel computing, but that's an advanced topic. That's why it's in parentheses here. Sandbox support. Some languages have their own sandbox, like Java and C#, but you also have operating system level sandboxes where you can lock the process into a sandbox so that if somebody hacks the software, they can't move back and forward. The availability of secure frameworks might also play a role. So if you plan to write a, for example, web application, it might be advisable to have a look at the frameworks that your language offers, and if there are some good and secure options, and if they have security documentation, and if they have a security contact. These are things, if they are regularly updated, if they have a list of known vulnerabilities, if they have a security mailing list. These are things that you can look into and you can use to assess whether it's a good framework. Great. So if you have chosen your language, you might have done that already, and you might be into, I don't know, Rust, and you don't want to change. That's fine if it does the job. But we learned some criteria that can be helpful to assess whether it's, you can write secure software with it for your purpose. But secure software can be written in any language, basically. We're going to look at some basic secure coding practices now. So some practices that will help you against certain vulnerability classes. And it's something that I think is one of it's a very basic thing to do and to learn. We're going to look at these. I picked out some where I thought they are important. We talk about input handling and output handling. That's one of the first things that will come to your mind when you think about security. So there's going to be input from users and possibly from attackers. What am I going to do with this input to secure my software against malicious activity, right? Output handling is more important for security, and we're going to learn why that is the case. We're going to get back to pitfalls in low-level languages. We're going to have a look at an example for a buffer overflow. Again, we talk about the principle of complete mediation. In modern environments, in modern software, on modern stacks, authorization is still the biggest problem of all. So this is why I mentioned this again. We're going to talk a little bit about cryptography. It's a very big and very broad topic, but just some hints that might help you get in the right direction. Going to talk about session management because it's detrimental to security if you have a client-server application of some sort. And we're going to talk about concurrency, but not parallel computing concurrency, but for example, two users are editing the same object on your web application, or you have parallel file uploads. How can I deal with something or two things happening at the same time? What are security vulnerabilities that can happen in that case, and what can I do about them? So these are the secure coding practices that we're going to go through now. And yeah, so input handling is the first thing. Input handling has many different major activities. It has canonicalization, it has input validation. That's probably the best known security activity or secure coding practice. And there's also something called sanitization. These three things do different things, and they should be done in a specific order. Let's have a look. First, canonicalization. I'm asking you, is someone at example.com and someone at example.com with an uppercase S, are they the same email addresses? I'm looking in the chat. Take your guess. So say yes or no in the chat if are they the same email address or not? I don't see any answers yet. I could make a poll. I'm going to make a poll. Give me 1 sec. So option 1, yes. Option 2, no. Start the poll. So we have the poll. Go to stage on the very top right, and then to polls. And then there's the poll. You can answer yes or no. We have 43 votes. 79% think it's the same. 77% think it's the same. Okay. I'll give you a few more seconds to vote. So go to stage on the top right and go to polls. All right, so we're going towards 75% yes and 26% no. You know what? The right answer isn't there. The answer is a clear yes and no. So if you look at the standard where email addresses are defined and their structure is defined, you will see that technically speaking, these two are different email addresses. So if an email server adheres to the standard, it would treat those two addresses as two different addresses. So you could register someone with a lowercase s and someone with an uppercase s, and then another one with an uppercase O, and then another one, you get the point. You can just do all combinations of upper and lowercase, and they would technically be all different email addresses. But people saw that this doesn't make a lot of sense because, you know, there would be a lot of confusion, and you would have to tell people, you know, my surname is written with an uppercase K, because otherwise that other Thomas Conrad is going to get the email. That wouldn't work in practice, right? So in practice, they are considered the same email address with, I think, every major email server out there. You cannot go and register a Gmail account with another person's name by just uppercasing any of those letters. So yes and no, with a tendency to, in practice, yes, they are the same email address. So why should we even care? Again, this is a software security talk. Why should we care about whether these two email addresses are the same? Well, the uniqueness of the email address is often important for security. If you have the email address as that central identifier for a person in your system when they authenticate, that is important, because otherwise another person could register an account even though the account already exists. So not canonicalizing the email address might make impersonation possible, depending on how exactly it's implemented. So we should canonicalize and bring it in the form where it's unique, right? In the case of email addresses, that could mean lowercasing everything, right? That's what we do, for example, in our system. So not canonicalizing might make impersonation possible in that very case. There are other examples where, you know, the same data structure can be typed in different ways. IP addresses can be shown as an integer. Try, everybody, open your command line and do ping, and then ping this address here. Just enter this number and see what happens. I'll give you 10 seconds for this small interactive demo. So enter your command line and enter ping space 213.070.6433 and hit enter. What's happening? So what's happening is that you're pinging this one, so 127.0.0.1. You see that IP addresses can be written in different formats. The same goes for IPv6 addresses. So if you have an IP address that is an input in your web application and you make security decisions on that IP address, you should canonicalize it before you store it in a database. And there are other data structures where the same happens. Look at this URL. You have https a.com without a trailing slash. You have it with a trailing slash, and we have it with an explicit port number. All those three URLs are the same. They lead to the same web page, but they are written in different forms. You can put the protocol there, you can leave it out, you can put the port there, you can leave it out, and so on and so forth. All right, so input validation is the next part. Canonicalization, the first one. Input validation. When you do input validation, you can check your inputs against certain formats. You can have a maximum length, certain allowed characters, it can be a date and time, and so on. So it is generally advisable to validate your input against these things, for example. Now you might ask yourself, does input validation help against specific vulnerabilities? Usually it does not. If there's one thing you take away for secure coding practices, please take this away. input validation does not help you against specific vulnerabilities. Why not? It's because you might have to allow certain characters because the application mandates you to do so. Think, for example, SQL injection, and you want to avoid SQL injection by disallowing certain dangerous characters, right? SQL injection is you have an input, that input is concatenated into an SQL statement that is used to query data from your database, and you just use string concatenation. You have one string plus user input. Now you could use or misuse the user input to change the structure of the query. And most of the time when the user input is put into the SQL query with single ticks, you need a single tick to break out of the context. So very, very often in practice, a single tick, a single quote is used to attack systems with SQL injection. Now, one could argue, let's just disallow single ticks or single quotes, and the problem is gone. The problem might be gone, but you might have another problem. First, there could be SQL statements that don't use single ticks, and you still have SQL injection. That's dangerous. And the other one is you might have to enter the single tick. Imagine my name is Mike O'Connell, and I have this single quote in my name, and the system doesn't allow me to enter those characters. That's usually a sign for bad application design if you rely on input validation to protect against certain attacks. Also, cross-scripting, disallowing these square or the greater than and lower than characters. I might need them in an input. I might have to be allowed to enter those characters that are dangerous in the target syntax. So to sum it up, input validation is a good generic countermeasure to lower the attack surface, but that's it. It's not going to help you against specific vulnerabilities, or it could possibly help you, but you will have other problems. You cannot just filter everything that's potentially dangerous. Then the people who wrote the requirements are gonna knock your door and say, we need that single quote in the input. It has to work. So output encoding is the key. Before we go to output encoding, just one question that I think it was also asked in the registration section. Input validation on the client side, is that okay? So to put it short, there's nothing wrong with client-side validation. So in your JavaScript code, for example, if there's a server-side counterpart that also checks the input. So with client-side validation, you save a round trip. So at every form post, when you click the register button down here, in a classic application that has only server-side input validation, that would mean you send the form data to the server, it validates, and going to send back the form again with all the errors. So there's a round trip through the server. It's just slower. If you do the input validation also on the client side, it's going to save you a round trip. It's going to be faster. The user is going to get a response way, way quicker than if the server or the application has to send the data back and forth through the server. So there's nothing wrong with it as long as there is a server-side counterpart to it. It's good for usability, it's good for speed, it's good for performance, but have both in place. That's the most important thing here. Output encoding. This is the countermeasure that gives you the protection against specific vulnerabilities, such as SQL injection and cross-site scripting. Now, what is output encoding? It's safely embedding user input. For example, something that a user has entered here in a form like this and sent to the server, embedding this into other data structures like HTML, like an SQL statement, like an email subject, like everything, right? You can take this data and put it in different data structures. Now, what you have to watch out for is that you have to encode characters that have a special meaning in that target syntax, like HTML. In HTML, we have characters like greater than, lower than, equal sign, double quotes, exclamation marks, dashes. All those characters have a special meaning in HTML. So if a user inputs let's say, they have a name and they're called O'Connell, right? And they have this single tick in their name. You have to encode it in HTML. So an encoded lower than sign would be and LT and semicolon. That's an encoded character. That will help you against the vulnerability, because that system that interprets that complete data structure afterwards is not going to interpret those characters as something that is part of the syntax. So we convert input characters that have a special meaning in that target syntax into an encoded equivalent. So we are avoiding the possibility to change the parent data structure and thereby attacking the system with SQL injection, cross-site scripting, and many other vulnerabilities. So what are common situations where I must be aware of the problem? I must be aware that I have user input and I put that into a bigger data structure, and that bigger data structure could be changed and manipulated. A classic one is HTML. So if you allow any character and just output it without any change and without any encoding and just by string replacing and concatenation, you're going to have cross-site scripting if you do that with HTML, right? If you do that in JavaScript code, the same could happen. Or you could go and embed your user input into an XML data structure and use it as a request to another system. Now, if you don't encode the special characters or the characters that have a special meaning in XML, like lower than, greater than, equals, double quotes, and so on, the attacker could change the structure of the XML document. They could add other elements to it and maybe do an attack, depending on the context. Depends on how exactly that works in the background. There are more examples on that. For example, LDAP, the Lightweight Directory Access Protocol, is used, for example, for authentication against Active Directory, the Microsoft identity solution. And that's a specific protocol that can use so-called filters. That's a syntax with parentheses and asterisks. You might have seen that already. Now, if you embed the username into such an LDAP query and you send it to the LDAP server to see if the user exists in the system with an LDAP search, you can have LDAP injection if you don't encode the characters that have a special meaning in LDAP filter syntax, which is parentheses, equals signs, asterisks, and some more characters. And the list goes on. So many, many, many vulnerability classes are there because people fail to encode user input for the target syntax that they're embedding that user input into. So output encoding as opposed to input validation, this is usually the primary protection mechanism that protects against specific vulnerabilities. Input validation is a great thing. It's a generic measure that lowers the attack surface, but output encoding is the key to software security. So this is, I think, one of the most important takeaways in combination with that input validation does not help you against certain vulnerabilities. So output encoding is the key. Now, there's a third kid on the block in input handling that is called sanitization. There might be situations where you take HTML as an input, right? In your application, you take HTML as an input, and you have to put it into a parent data structure that is also HTML. So you cannot encode. Look at this example here on the right-hand side. If you see a web application, that's basically, if you see that, that's a very, as a penetration tester, if I see this in a web app, I already, it smells like cross-site scripting. I can already smell it. So you have HTML in the background. When you format text here, there's a link in here. There's another link. You can use unordered lists, and you can make stuff bold and italic and so on. What these editors in web apps usually do is that they convert this text. It's not just a string of text. It's HTML in the background. Now, if you take that and embed this into parent data structures like HTML, you might have cross-site scripting, because an attacker could just change that HTML code and include a script tag, and thereby execute script code in everybody who reads that text, right? So if you see this in application, go and look for cross-site scripting. Now, in this case, we cannot just encode, because we're gonna see HTML syntax in our output, and we don't want to see. We want to see the formatted text. In this case, we must get rid of the dangerous parts. There is no other option. So those parts of HTML that can contain JavaScript, that's script tags, that's JavaScript event handlers. This is called sanitization, right? Sanitization means I take a potentially dangerous input, which I have to use in that way, and that cannot just encode that input when I put it into another data structure. And I strip out everything that might contain JavaScript in that case. I'll really fancy a cocktail right now. They have the cocktail sanitizer over here. Don't roll your own sanitizer is the rule of thumb here. Don't just do that on your own, because this is really, 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 really hard to do. Use libraries that are specialized in this, that are designed to do sanitization securely. There's a good one in JavaScript. It's called DOM Purify. Angular, as a single-page application framework, comes with its own sanitizer that's somewhat limited in its functionality, but it does a good job in protecting you against cross-site scripting. In the PHP world, there's HTML Purifier. There's the OWASP Java HTML sanitizer for the Java world. There's HTML sanitizer for C#, and so on. So if you search for HTML sanitizer in your programming language, you're probably going to find a sanitizer that does the job. Don't do this on your own. Just as much as you shouldn't roll your own crypto, you shouldn't roll your own sanitizer. That's potentially dangerous. So let's put all this input and output handling into a bigger picture. If here in the middle we have your application code where you process the data. If the data comes in from the user interface, that could be a web browser, for example, the first thing you should do, that if it's necessary and if it's a data structure that can be represented in different ways, you should canonicalize it. So bring it in a format where you can compare it for uniqueness. Think email addresses, IP addresses, URLs. Important to canonicalize them so that they have a specific target format. That's not necessary everywhere, but in the cases we mentioned, it is necessary for security. Then you should validate the data and see if it fits your target scheme. So if it's a valid email address, or if it's actually a date, or if it's a Boolean value or a number, and so on. So this is basic validation. Again, this is not going to help you against specific vulnerabilities, but it's going to help you to lower the attack surface. If you have a number as an input, and that number is used in an SQL statement in an insecure way, and there's SQL injection, if you validate that it's really just a number, an attacker cannot exploit it because there's no single quotes or anything you could put in there, or it's very hard to exploit this. Validation, a good generic attack surface reduction measure. And then if it's necessary, for example, if you have something like HTML input, go and sanitize it and strip out everything that might contain JavaScript in that case. Then you store it. And then when you output the data from the database, do context-sensitive output encoding. Context-sensitive means with regards to the target format. So you might use the name in an API response in a JSON structure, or you might use the name in a CSV export, or you might use it to send a text message, or you might send an email containing it, or you might embed it in HTML and render a website with it. Whatever it is, make sure to know what output encoding or how it works for your target format, and then put it into the data structure. This is the measure that helps against specific vulnerability classes, right? If you think about this, for example, in the HTML world, and you render HTML pages, make sure to use a templating engine that does output encoding automatically. Because if you have hundreds of variables throughout your application, you embed that in HTML, it's very likely that you make a mistake here or there. So make sure that this is done automatically by the system, by the framework, for example. This is typically something that frameworks come with and do for you. Great. Again, secure coding practice. We talked about this in the beginning as well when we looked at the features of programming languages. So potential vulnerabilities in non-memory safe languages are buffer overflows, heap overflows, format string vulnerabilities. All of these can be used to take control over the program flow. So these are potential vulnerabilities. This is what a classical buffer overflow might look like in a C program. So you have the string copy functionality that copies this buffer into this one. And you see that this is a user input that can have an arbitrary length. So if you create a buffer with just 10 characters, and this buffer here is longer than those 10 characters, then the program will just continue writing. So it's going to write into those 10 characters in the beginning and continue writing until the input buffer is over. And after that, that buffer that's declared here, there might be some control structures that control the flow of your program. And an attacker can override this and take control of what the program is going to execute. That's called a buffer overflow. That's a very classic and simple example here. Now, what is the problem? Or why is that even a problem? In memory, so in your RAM, when you execute a program, we have a mixture of data and code. So there's code that is executed by your CPU, and right beside that code, there is data that you input as a user or that you read from a file or whatever. And then there's code again, and then there's data again. So it's a mixture of those two things. And that's, of course, by design a bit dangerous, because the program might write beyond the memory area of that data structure. So overwriting these control structures that are used to jump between different parts of your code in the execution flow, an attacker can misuse that to take control. What can we do about this? So what's the secure coding practice? Don't write beyond the buffer, do bounds checks. So if you have a buffer of 10 characters, make sure that the input cannot be any longer than those 10 characters. So always be careful with user input. In C++, there are some classes that manage that for you. So there's a string and vector classes that are not susceptible to this problem. There are unsafe methods like string copy or mem copy that are by design susceptible to this attack. There are bounds. So in the newer versions of the C and C++ standards, there's a description of bounds checking interface. So it's those method names that, for example, strcopy_s, and you have to pass it the length of the input so that bounds checks can happen automatically. So in C and C++, it's hard to protect yourself against this problem. So you have to be very careful and have to really know what you're doing. In languages like Rust and Go, they have memory safety by default, but they have also these unsafe spaces where you do have pointer arithmetics. So stay in a safe world unless you know exactly what you're doing with those newer languages like Rust and Go. We'll get back to the principle of complete mediation. I mentioned that in the core design principles in the beginning. It means access control at every request. If you design a software like a web application or API, just suppose that the user knows all the URLs, they know all the parameters that are valid for this purpose. Be also careful with multi-step forms. So there's a form where you enter data, you click next, next step, click next, and so on. Make sure to make the access control at every single one of those steps in the form, because I might just be able to jump to the third one without access control. It's also important to think about the design of your access control very well at the beginning and have a centralized implementation, and don't spread your access control measures. Some are in the templates, some in the controller, some in the configuration. It's going to be very hard to assess whether this is secure and well done, right? So make sure to really make this solid, centralized, testable. We will quickly talk about cryptography. This is a very broad topic, but just want to give you the most important information about it. So in cryptography, we distinguish between three kinds of things, right? It's cryptographic primitives like block ciphers, stream ciphers, hash functions, public key primitives, so asymmetric cryptography. And these are the basic building blocks for cryptography. So block ciphers, stream ciphers are usually used for encryption of data. Hash functions are used in different ways. They can be used to, for example, in digital signatures. They're hash functions that we use. For securely storing passwords, we use certain kinds of hash functions that they are one-way functions. So you have an input and you have an output that's always the same size. For passwords, we use expensive hash functions that are done multiple times in a row so that brute force attacks on the hash are harder to do. Then there are cryptographic schemes that take some of those building blocks and put them together to reach a certain thing. For example, symmetric crypto systems that do the actual encryption, or message authentication code that use a hash function in a certain way to do symmetric signatures. And then there's protocols that use different schemes and primitives all together to reach a bigger goal, like TLS, that we all are using right now to securely transfer the data from the Hopin server to our browsers. There's a TLS tunnel that is used to encrypt the data on the wire, so no one can read it in the middle, right?
or SSH is another example for that. Also, SMIME can do encryption of email messages and digital signatures of email messages, and they use different schemes to reach that goal. So just for, this is the cryptography world from a very high perspective. When it comes to encryption, there's a lot of misunderstanding, and there's a lot of people trying to throw encryption at something and not reaching their goals. Now, there's one word, new kid on the block, that is everywhere and everybody talks about it, and few people understand what it really means, my impression. End-to-end encryption. What is end-to-end encryption? End-to-end encryption means that when, for example, I want to write a message to one of you folks with a messenger app, let's take Signal as an example because they have end-to-end encryption, then it's not just the tunnel from my web browser or my app to the Signal server that is encrypted, that's encrypted network, but also the message itself is encrypted so that only you can decrypt it on your device. So I encrypt everything here for your device specifically. So even though somebody has access to the server, they cannot read what's in that message. They can see that I sent you a message, but they cannot see what I sent you. That's end-to-end encryption. So all the key management, everything is on the devices of the users, and it's not on the server, right? It's on the devices. So I encrypt it here, and only you as a recipient can decrypt it. That's end-to-end encryption, not just transport encryption like TLS. Now, people seem to want to have that for their applications and for their software. I would tell you that in very few cases, it is really advisable to do so. Why? Now, we can have encryption on different levels. Sometimes you will see in requirements documents that somebody says, we need to encrypt data. And we have to do something that we can check this box. Most people that write this don't understand what it means to encrypt data or what options we have to do so. There's the lowest level encryption would be disk encryption. So on your server, there's a hard disk in there that has transparent encryption like BitLocker or FileVault or anything like that. That's completely transparent to the application. This helps me against somebody running into the data center, pulling out the hard disk and running away with it. That's the attack that we're protecting against. If somebody hacks your application and goes in through the front door and does an SQL injection, it's not going to help me at all. Zero. So it's not going to protect me against this kind of attack. And somewhere in the middle, we have some of the database level encryption that helps if some other user on the operating system is trying to access your database files. Also, a little bit more sophisticated attack. Then we have application level encryption. So we have encrypted data in the database, but the application, so the server is managing the keys. It's getting harder already. And then somewhere on the very right-hand side, we have end-to-end encryption. This is when your client devices, your web browser, your smartphone app, they are managing the keys. Now, this is the best protection for the data, of course, but it's also very, very hard to do if you think of it. So if we try to put this into another dimension where we have the y-axis, we have the solution complexity, the more you go towards end-to-end encryption, the more complex the solution is going to be. And it's going to be very, very, very much more complex. And don't underestimate how complex this can be, because you have to think about all those things. You have to think about when a user loses their device so that they can access their messages. What happens? How do you recover keys? Do you store them somewhere on the server side? Well, then an attacker can have access to those keys as well. How are you going to do backup in a secure way? Right? Signal is having issues with backups because they're asking you for a PIN every 2 weeks, which is very cumbersome. Psychological acceptability, no good. How are you going to handle multi-device? So if I have multiple devices, I want to use Signal on my laptop and on my smartphone and on another device. Everybody knows that this is really hard. You have to scan a QR code and then some magic happens in the background. So if all those things are encrypted, it's hard to transfer them to another device. If you don't have end-to-end encryption, you can just log in and see all the data, right? So the more of those things you have, the harder it gets. Also, you cannot index the database. You cannot search in a message because you can only search on the client side because this is the only place where you have all the messages in clear text. There are ways to also search and index encrypted data, but there's a lot of research being done on that, but it's not like it's ready for production now, right? It's very hard to integrate yet. Also scalability. So if you scale out and you have many users, these are hard things to do. So if you want to do end-to-end encryption, think very well if this is really what you want. You probably have bigger problems, and it is advisable to fix those first and to care about the basics of software security before you go into the most advanced topic of end-to-end encrypting personally identifiable information. So cryptography, important rules. This is not a complete list. Cryptography, is complicated. So I just have a few rules that I think are advisable. Don't roll your own crypto. There are crypto algorithms out there that are good. Don't just check the encryption checkbox by enabling Disco database encryption. Be aware of what you're protecting yourself against. When I do design and architecture reviews and people say we encrypt this and that, and then I start asking questions, I really quickly notice that most of those people have not thought about why are we doing this? Is this only for compliance reasons or because somebody expects us to encrypt data? If you lock the door and you have the key right beside the door, then it doesn't really help you. And this is what most people do. They encrypt something and the key is right beside it. Doesn't help you. Use good randomness, because if randomness isn't good, encryption and all kinds of cryptography boil down to something deterministic and breakable. So good randomness is key here. If you use symmetric encryption, use AEAD ciphers. Authenticated encryption with associated data. It's, for example, AES GCM or ChaCha20 Poly 1305. What a weird name. Use unique initialization vectors if you reuse keys. So if you use the same key, like the Signal app uses this, it has this key rolling mechanism, but if you use the same symmetric key for multiple times, use initialization vectors for that purpose. If your key base is a human-generated password, something that I made up with my memory, use expensive key derivation like Argon2. Don't just use a hash or something like that. Good crypto is really hard. Get help if it is necessary, right? Don't just encrypt something with some algorithm and some key. Think about what exactly is that what you want to protect yourself against, because it is very dangerous that you run into a situation where it makes everybody's life harder, but it doesn't protect against anything. And I see this very, very often, more often than not, right? So good crypto is hard. Get help if that is necessary. A few more secure coding practices. Session management. So what is session management? If you have any client-server application, like for example, a browser application and an application server on the other side, and they are physically separated, you have to maintain some sort of session. So the user logs in with their credentials, maybe multi-factor authentication. They get back a session ID, and that session ID is then used to make security decisions on the server side, right? The user is not going to re-authenticate or enter their password every time they click on a link or they submit a form in the web application. That has to happen automatically in the background. And this usually happens with so-called session IDs. They are randomly generated sessions that are sent to the application server upon each request. And that session ID is stored somewhere here. So it says session ID 123 something, randomly generated, is connected to this user, and they have this and that role. They are administrator or they are not administrator. So it's all stored here in a centralized session storage. And at each request, for example, the user wants to submit a form, application server is going to check the session here, say, does the user have the permission to submit that form? If they have, application server processes the request. If they don't, they send back an access denied response. So each request is basically stateless, and in order to maintain this state over multiple requests, we maintain a session here on application server once the user has logged in successfully. So some important rules. If you use a framework, use the session management of the framework because it's usually solid and well tested. Make sure that the session IDs are non-guessable. That could be random session IDs, just a random string. I would suggest at least 128 bits of entropy if you want to know a certain length of a session ID. The session ID is the only source of information for security decisions. Again, if I go back, if I go back to this slide here, if the user sends a request, The only way I make a decision whether or not that user can do that action is the session in here. Does the user have the role to do that? Never trust anything that comes from this side, like a parameter that says admin equals true, or the refer, or the origin header, or any header that's in the HTTP request. Because any part of the HTTP request can be manipulated on the client side. So the session on the server side is the only source of information for security decisions. Make sure that the session ID changes upon a successful login. So many applications have the concept of anonymous sessions. So you access a website the first time, it's going to issue a session ID that has no actual session with a user. It's just an anonymous session. When you log in, that session ID should change. It should be regenerated. This protects against so-called session fixation attacks. So you can Google that if you're interested. Check your own application if it actually changes after you log in. Also important for security is have inactivity timeouts and absolute timeouts implemented and configurable. The thing is, it might be you might code an application that has very, very, very sensitive data, such as an e-banking application. And e-banking applications usually have very short inactivity timeouts. So if you don't do anything in application, you don't touch any button or anything, or any link, it's going to log you out after 15 or 30 minutes because it's very sensitive stuff in there. It's about having or losing the money that's on your account. If it's less, dangerous or less critical data in there, you could just as well have an inactivity timeout of multiple days or even months, depending on what's in there. But you should have these timeouts implemented, and you should be able to configure them in your configuration files. There's also a related talk on sec4dev. That's the first talk tomorrow morning at 10 o'clock by Philippe Derek. He is probably one of the best web security instructors out there that I know. And he's really, really good at getting the point across. And he's in the defense world, so he is not a pen tester that actively tests the systems. He is developer himself, and he really knows how to explain things. He's going to talk about token security in single-page applications, so how to store and manage security tokens, like, for example, session IDs or JSON web tokens in web applications. A really good speaker, highly recommended. A few more secure coding practices, and I'm going to make a short break. Sequential or concurrent programming. So there are different words here just to get to be able to distinguish those things. There's sequential, there's concurrent, and there's parallel. Sequential means that if I have two queues that want to execute something, that I execute the first queue and then the second queue, and then we're done. Imagine you have a coffee machine and there are two queues. The first queue makes coffee first and then the second queue. That would be sequential. Then there's concurrent. Concurrent doesn't mean actually at the same time. Only one thing can be processed at the same time, but it means first person of the first queue, first person of the second queue, and so on. So we change between those execution queues. And parallel computing means that I have two completely independent queues. I have two coffee machines, and I can process those two queues in parallel. So just to start this topic, to be able to distinguish the terms. In terms of concurrency in applications or software design, I want to discuss two situations. I don't want to discuss you have distributed parallel computing for performance reasons. That's an advanced topic I'm not going to cover here. But I want to discuss these two situations. Imagine, for example, you have two users that use the same application. For example, they use, a recipe application, and they use the admin backend to, post new recipes in there. Now, suppose two people want to change an existing recipe, and they open the web page, they click the edit button of that recipe at the same time. So two independent users have the same tab open in their independent web browsers. Then they change something in the title, user A changes something, user B changes something, and then within 1 second, they both hit the save button. Now, what happens in such a case? The user that comes later is going to overrule the edits of the other user. So that's the first situation I want to talk about. And the second situation is there might be transactions that may happen simultaneously. And imagine, for example, a bank transfer where there might be transfers from the same account more or less at the same time. So I transfer 10 euros from that account, and another person does that as well. So a situation that does happen regularly, or you have an upload of a file that you chunk the file in several small pieces and upload them in parallel. So there's going to be many concurrent requests happening on the server side. So the first situation is maybe a little bit less likely because it has to happen that two users either just edit the same object at the same time, or there might be something where there a situation where this parallel processing will happen. Let's have a look at this bank transfer example. Say we have $10,000 on that account, and this first function call, or this first request, wants to withdraw $10 from the account. There's another thread that wants to do the same thing. Now, as these two things cannot happen simultaneously, the CPU might be processing this part of the function first from thread 1, then it switches over to the second thread, transfer or executes this part of the code, and then it switches back to the first thread and processes this part of the code. We withdraw $10 here, and we still have a balance of $10,000. It calls the getBalance function, gets 10,000. Then it reduces the amount from the balance, so 9,990 is left. And it echoes, you have drawn that amount. Now, the other process or the other thread kicks in and does the same thing. So it calls the withdraw function. It gets the balance. The balance is still $10,000 because this function call here has not yet written the new balance into the account because the other thread took over. So we still have 10,000. We reduce the balance by the amount. And then this execution here sets the balance to 9,990 because that's what the calculation resulted in. So we subtracted $10 from the 10,000. Then the other process, this set balance function call, kicks in again from thread 1 and sets the balance to the same amount. So we reduced, or we wanted to reduce the amount on the balance on the account by $10 2 times. But what we did in the end is that we subtracted it only once, because these two processes did the time of check here and the time of use here concurrently. And at the same time, we have a so-called race condition. We have a race window in here. So this is a real-world non-code example of a race condition. Don't be happy, worry. It's basically the same idea. I have to order that T-shirt. I think it's still, you can still order it. I like it. So what are solution approaches to this one? So if you have the situation where you have concurrent or two things on the same object can happen concurrently, you have to ask yourself, is this concurrent happening of this execution the rule or the exception? If you think of the recipe application admin interface where two people might be accidentally editing the same recipe, well, then one person uses their edits might be something that doesn't happen all too often. So we can be optimistic about that. It's not going to happen every day. Or is it the rule, like in the bank withdrawals? A bank needs to be aware of the fact that two transactions might happen at the same time on the same account. So that's rather likely comparably that this is going to happen. What are possible solutions to this? For the optimistic case, think of the recipe application. Two people are editing the same recipe. It could be versioning of the recipe. So every time you edit something, you increase the number, and you send the number of the version with the form submission. Now, if on the server side, you notice that the version of that recipe has increased in the meantime, you can send back an error and say, look, I'm sorry, but your changes are lost because somebody else edited. You should reload the recipe and edit again, so that at least they don't expect their edits to be in the system and they at least get an error. So that's the optimistic case. Now, in the more pessimistic cases where this situation will happen sooner or later, you should watch out that you do atomic operations. Atomic operations mean that the time of check, so when you read the balance from the database, and the time of use when you write the new balance back to the database, these two should happen within one atomic transaction. So that we cannot have the situation where check, use happen this way. They should happen always sequentially. I had this very situation recently in my own piece of software where I asked myself, what the hell is happening? And it was exactly such a time of check, time of use problem. It was as follows. So I have an application where I upload a file into a web application, and I split that file into several small chunks. On the server side, I have file locking, where I put this chunk into the file on the file system. Now there's a counter that increases the number of chunks that have been uploaded. And I had exactly a situation where I read the number of chunks that were already uploaded, and uploaded the file, and then I wrote the number of chunks uploaded +1 back into the database, but later. So, and I have 5 parallel uploading threads. So there will be a situation where I have this time of check, time of use problem. Now I changed the software. Instead of I read it from the database, I process something and I write it back in the database. What I do is I have one single SQL statement that reads and writes at the same time. It goes like update the number of chunks uploaded equals number of chunks uploaded +1. So one atomic database operation, and the database itself is going to manage that and is going to take care that this operation can only happen, one at the same time. So I changed from time of check, time of use being separate into one transaction. That's one possibility to get rid of the problem. Before, I had only on average, about 60% of the chunks actually counted in my situation. And after the change, 100% of them counted. So I eliminated that race window. You could also work with mutual exclusions. Be aware that this sometimes doesn't scale so well. So file locks and row level locks in databases, they can be slow. So it can be you write something in a file, and while that one process is writing, the other process has to wait. And then when this process is done, the other one can do that. So you might get in a situation where many processes are waiting to be able to write into that file, and it probably doesn't scale so well. Message passing is something that a colleague made me aware of yesterday. You could have one centralized single process that does that operation of writing stuff in a file, and a queue in the middle. So everybody can push stuff in a queue, and that one process that is just responsible for that atomic operation processes the file writes one after the other. That's another approach that probably scales a bit better than locking. So that's it for secure coding practices. Let me sum up this chapter. So we had input handling that consists of various different steps. We had canonicalization, so make sure that if the same data can be displayed in different ways, that you have it unique, you have it canonicalized. Then input validation is make sure that the input is the way it's supposed to be. It's not going to help you against specific vulnerabilities, but it's going to help you to reduce the attack surface. And we have sanitization, which is necessary when I have, for example, HTML as an input. I cannot go and encode. Speaking of encoding, output handling or output encoding is the one security practice that tends to help against specific security vulnerabilities. In low-level languages, I have to take care about memory management and pointer arithmetic so that I don't have buffer overflows and format string vulnerabilities. So make sure to really understand what's going on over there. The principle of complete mediation means access control at every single request. What I told you about sessions and the fact that the application has a centralized session where it does security decisions on, make sure that this is the only source of security decisions. Cryptography, make sure to understand what's going on. Don't just throw encryption at something. Make sure to understand what's the threat you're protecting against. This is a source of a lot of misunderstanding in my point of view. So make sure to get external help if you want to, design your system in a way that, it protects against certain threats. Session management is something if you have two components, one public, for example, web application that is accessed via a web browser, and you have a server component, there needs to be some sort of session so that each subsequent request after the authentication can be authenticated on the server side without sending my username and password every time I submit a form. There are a few things you need to watch out for. If you can rely on the session management of your framework, they usually do it well. Concurrency, we looked at two situations where either two people are editing the same form in a web application, or I have some sort of parallel execution, and there's this danger of having the time of check and time of use separated, and I have two processes that execute those things in this way, and then I might, the integrity of the data might be in danger, which I personally had to fix exactly such a problem recently with parallel file uploads and counting how many were already uploaded. So we discussed a couple of solution approaches to this. All right, so we have the secure coding practices. What's still up for today? So we want to talk about the secure software process, so not just the coding part, but things left and right from them. Please make sure to tune in after the break. We will make a break until 11 o'clock from now. So that's about 7 minutes of break. Open the window, get some air in, get a glass of water. I'm going to do the same and see you back here in 7 minutes at 11 o'clock. Thanks for watching so far. All right. So back we are. Just to clarify one thing about type safety and Python, I was wrong in one specific aspect, and you were right, the people in the chat. So Python is dynamically typed, but it's still strongly typed. So that means that those implicit casts, like they happen in PHP and JavaScript, where I can add an integer to a string or the other way around, is not possible in Python. But still, you don't declare that this is an integer, this is a string. It depends on the first assignment. So it's a little bit different. And there's lots of shades of gray in dynamic typing, strong and weak typing, static typing. The stricter the language, the harder it is maybe to create software with it, but the more long-term advantages it might give you also in terms of security, at least, in terms of static analysis. All right. So thanks for clarifying this, Daniel. You are right. Great. Before we move into the secure software development process, I want to talk about clean code. Now, you might ask yourself, clean code, security, is this really related? I do think it is, and I'm really strongly believe it is. So why should we even bother? I'm going to ask you a question again, and I would suggest you write your suggested answer in the chat. If you want to assess the security of a piece of software that you have not written on your own, what is the most important prerequisite for you so that you're able to do it? What do you need to have about the software to be able to assess its security? What do you think? Please write your answers in the chat. What do we have to have about the software in order to be able to assess its security and understand its security? I see people write depends. No, that's a different answer. Stage chat. Clarity of what's written. Yes. So that's one point of it. Any other takes? Security requirements. Yeah. Helpful. Requirements. There's 164 people. I want more answers. Come on. What do you think if you have a piece of software and you want to assess whether it's secure or not? What do you need about it? You understand what the code should do and what it's intended to do. You have to have the source code. Yeah, that's a clear thing. Yes. Knowledge of the environment. So these are really, really good points. You need to have, you need coffee. I need a coffee as well. I didn't have enough time. You need solid understanding of its functionality and the context in which it is running, right? Threat model is part of that understanding. So what security posture are you wanting to give in a piece of software? You need that. The least thing is you need to understand how it works. This is why when we do penetration tests, we usually spend at least a couple of hours and we ask the people who wrote the software to explain to us what it does. not only security-wise, but also functionality, also requirements. What is maybe the threat model and the security posture that you have in that piece of software? So all of these pieces of knowledge around it are important to be able to assess it, right? System architecture, very important. Architecture documents. How is this going to be deployed, and how is it going to be running? What other systems, where is it, is it publicly reachable? Is it just in an internal network? Are there any other systems that call this software to do things? What privileges does this other software have? All these things are important to assess the security. Now, unreadable code tends to be more insecure because nobody's able to understand what it does. If you think of systems, for example, like, let's take as an example Microsoft Windows. There are design flaws or there were design flaws in the system. For example, the pass the hash, where you could authenticate yourself towards another Windows system by just using the hash of a local user if that same user existed on the other system. That has changed recently, but that was a long-term flaw that was in there. Now, why did people only realize that this flaw existed so late? It was not, people didn't realize, it was not coded and then the day after they said we have this threat. It is because somebody understood with the security perspective only so much later how exactly the system works that they were aware of this flaw. So understanding how exactly things work is a prerequisite to understand. And unreadable code tends to be harder to understand. So nobody will find those flaws. So no understanding about this software means creative thinking about how to circumvent the measures, the security measures in there is an impossible thing. I remember having done security reviews or source code reviews where it took me weeks to understand and to look through how it is structured. And that's detrimental to, it's bad for security. So unreadable code adds to your technical debt. So if you have a prototype that is low quality code, but has a working example that you can show off, throw it away and start over when you write the software for real. What are some principles of readable code? I'm quickly going to go over them. Single responsibility. So if you write a class or a library, make sure that there's only one functionality. If you think about some software projects that have been around for a long time, like SSH, like Postfix, like those pieces of software, they all do, or I don't know, cannot think of a good example. They do one thing and they do it well, right? It's those pieces of software that do one thing and do it well that are there for a long period of time. If you try to pack too many things into one piece of software, they tend to, they tend to be hard to be assessed for security. It should be well structured. That's a pretty obvious thing. When I write code or write a class or a functionality in my software, then what I do is I try to make it work. And then when I have it work and I have a working test, a unit test that tests, or a functional test that tests the functionality in an automated way, I make the test green. And then I start refactoring. I start renaming functions. I start carving out functionality in separate classes. I start restructuring and shuffling things around, and always with an eye on the test that it's still green. So I think that's a very good approach, is that when you're done, you're not done yet. You should go and refactor to make it readable. So first, make it work. And I call this tunnel drilling. So I want something that I haven't done before. I want it to work first. And then when the tunnel is drilled, when the hole is drilled through the mountain and I see the light on the other side, I want to make the tunnel beautiful. And I want to make it so that cars can actually pass through and that other developers can read the code. So spend enough time on refactoring. Thoughtful naming. This is really, really important. It's a way underestimated thing. So if you have a variable that carries the current date, or I don't know, it carries the name of a person, don't just call it X or A or V. So make sure that these variable names are talking to itself, and also that you can understand what they do when you're reading the code out of context. There might be a function that is so long and you have this code block at the bottom and you have this variable that's called X. If you don't read the whole function, you're not going to understand what X is all about. There's really, the program is not faster if the variable names are shorter. I promise you. It is not the case. It is not it is not going to degrade the speed if you have long variable names. I tend to have very long variable names, but they're at least speaking to themselves. Good and readable code is simple. So make sure to not pack stuff in there that's not necessary in that case. Keep stuff as simple as you can. The comments should, in an ideal world, you don't even need comments because the function names and classes speak to it for itself, but I don't think that's quite realistic. So I do put lots of comments also in my code, but they should not explain what is done, how it's done, but why it is done this way. So there might be a piece of code where when you look at it out of context, you might ask yourself, I don't know why this is done this way. Then a short comment can really help out and say, okay, we're doing this because we want to protect against a certain vulnerability in this case, for example. Something I referred to in the beginning is continuously refactoring. Modern IDEs give you really, really good tools to refactor your code, rename functions, to carve stuff out of classes into separate classes, and so on. This is a very much underestimated task. So if you have a working software, you're not done yet. Go and have a look at the structure from a higher perspective, step back and see your class from 5 meters. And if it looks well structured, that's good. If it doesn't, go and refactor, and while keeping the test screen. And of course, well tested. So tests mean you should write unit tests or functional tests or integration tests that your code is actually doing what it's supposed to do. I remember myself, starting out as a developer, you just do, if you do stuff, I remember myself starting out and not writing any tests. And that led to a situation in the long term where, I was always afraid that when I did a change in the software, that it would break other functionality. And now we changed that strategy, and we have lots of tests that do that automatically check if the functionality is still there as expected. So it basically simulates the front end and sends HTTP requests and sees if everything behaves like that. With that, again, that's something that takes away initial velocity, but it gives you sustained velocity. I'll give you a concrete example. I'm coding software in a web framework, and there was a major version upgrade, maybe I think 2 years ago. And we wanted to upgrade to that version. There were a few breaking changes in that framework that didn't just permit to swap the framework version and that's it, but there were lots of changes that affected our code. And as we had a good code coverage with our unit tests, that meant we upgrade to the new framework, we let the unit test run, all the tests fail because there's some central functionality that breaks, right? You look at this functionality, you change it to work with the new framework, and then at once 30% of the tests turn green, and the other 2/3 we go about fixing those smaller places in code. So we managed to do a major version upgrade in the PHP Symfony framework, in that case, in half a day. And imagine if you don't have any tests that check the functionality of your software, there would have been many, many bugs in there that we would not have discovered without any unit tests. So it did take out some initial velocity, but it gave us sustained velocity by being able to upgrade to newer versions without so much hassle. So in the long run, this really saved us a lot of time. But in the beginning, you just want, you want software to work, you want it to run. But it's very important to also think about those tests. A book recommendation on clean code. I read this book, I think a year ago, a really well-written book on how to produce clean code, and some of these principles are described in there. It's by Robert C. Martin. It's called Clean Code. It's a very clean book as well. Clean cover. Great. So we've talked a lot about coding now. Coding is not the only thing that's important when you think about creating secure software. There's lots of activities around that you can do or should do, some of them, to improve the process of developing secure software. It's not just the coding, it's other things as well. Oh, that was wrong. Sorry for that. I pressed the end button and I landed at the end of the presentation, but it's not over yet. It's not over yet. So what we will take as an example is the OWASP SAM. Now, the OWASP SAM is a maturity model that you can use to assess the security of your software development process. It's not just the coding part, it's also stuff that happens left and right and above and beneath the coding. OWASP is a project, it's called the Open Web Application Security Project. And it's a project that collects resources for the secure development of web applications. It also now has, for example, threat modeling guide. It also has mobile application security guides. And it has the SAM, which is the Software Assurance Maturity Model. And it is basically a collection of activities that you can do in your software development process in order to secure your software. And it goes beyond just the coding and the vulnerability perspective. It goes into process perspective. How does this work? So there is an interview guidelines, basically an Excel sheet where you have interview questions, where each of these questions relates to one of those activity groups here. So if you go into this, for example, there is a more detailed view, a couple of questions that you can answer. And for each of those activities, for example, do you do any, I don't know, static application security analysis or something like that might be one of those questions. And you answer, yes, I've done it once, or I'm doing it for most of my projects, or I'm doing it for all of my projects. And depending on your answer, you get a different score. So you get a score between 0 and 1, and these scores add up in each one of those areas. You know, it's a prescriptive model. It doesn't mean that if you look at this, you should do all of those. It doesn't mean that you should reach the maturity level of 3 in each of those activity practices. It means that it serves very well as an inspiration for what you can do. And you should look at it as, for example, you pick out a certain question, say, am I doing this? No, I'm not doing this activity yet. The second question is, does it make sense for me? Is it something that I can implement easily, or is it something that I've already tried out and it works for me? If yes, then I maybe should do this activity first, right? It does not make any sense to reach the best level of maturity in any of those activities. That's the harder part. Going through the interview questions and answering those for you is the easy part. The harder part is interpreting the results. By the way, we as a software security team do also help organizations in interpreting those results and say, okay, this is maybe what's going to give you as an organization and the way you work, and the way you create software, the best value, because you have a language that's statically typed and that's very well testable with SaaS solution. That's something, just say something at random, and that could make sense for your case. But I don't know. Maybe another sort of test, dynamic application security testing, is not so good because it doesn't work so well in that environment, and so on and so forth. So it really depends on your environment, but it really serves as a tool for giving you a broader perspective on software development. I really recommend everybody who creates software to take this interview Excel sheet. You can download it on the website, owaspsum.org. And answer those questions for you. Don't be scared about if the score is low. It doesn't, it could mean that it's okay in some areas. It could mean that there's really a blind spot that we never thought about and we should change something about it. This is how you should approach this model. I'm going to pick out some of those activities now as examples that are typically useful, but it doesn't have to mean you have to do them, right? It could be useful. That's all I want to say with it. There's a great talk from Sebastian Delaire-Snyder from Belgium. It was at SBA Life Academy. You can find it on YouTube. And it gives a great overview of OWASP SAM version 2 that was launched last year. And he's one of the project leaders of the project. And he's also a really good speaker. So make sure to check out this talk for an overview. It was given in May last year when the pandemic started. There's also a related talk it's tomorrow at 5:15 p.m. That's our keynote speaker, Tanya Jenka. She's going to talk about security metrics that matter. So if you switch back to the OWASP Sum, there's a whole section about strategy and metrics. So how to measure if I'm getting better at security. And Tanya is really into this topic, and she knows what matters and what doesn't. And I really suggest you to see that talk tomorrow. A term that you hear a lot when it comes to securing your software development process is shifting left. Now, what does shifting left mean? Shifting left means if you spawn the software security activities in the circles like they are here on the slide, what people usually do is that they run and maintain software. That's what everybody does, right? I write software and I run it. Now, the further left you go, the less people do those activities. So a solid test strategy. Also thinking about not just the coding, but also the design and the security requirements. So the further left I go, the earlier in the process I think about security, right? And if you're here, you code something, and then you do maybe a security test, a penetration test. That's more of an ad hoc approach to software security. If you don't do tests and you just run it and see what happens, and there's an incident and maybe somebody hacks the software, there might be an incident, and there might be CISO intervention. We're in the ad hoc world. So what we want to do if we want to have a solid process in software development is shift left. Left means earlier in the timeline. When I write my requirements, ideally, security requirements play a role already. And ideally, I have security aspects of functional requirements in there, right? That's what is meant by shifting left. Also, a talk that is related, that's the closing note on Thursday, same time as the keynote tomorrow, making the promise of DevSecOps a reality. So everything related to security automation. Alyssa Miller is a specialist and also a really good speaker. We managed to have lots of international speakers this year because virtually we don't have to fly them across the ocean, which is a good thing for the environment and for the conference. One of the first parts of the OWASP Sum, the first security practice groups, is education and guidance. So when it comes to security, understanding your environment and understanding the vulnerability classes is key. You won't get security by just throwing a tool at your software. You will get some findings, but whether or not they make sense or not, the interpretation of the results, you need the knowledge about what is happening below the surface. So people sometimes tend to just throw expensive tools at their software, while they could have found those vulnerabilities in cheaper ways by maybe using specific open source tools for this and that vulnerability, maybe do a quick threat modeling session to find this and that threat, and maybe, so it's really important, and that's the first thing. Learn about security, learn about coding. The development of a developer towards something that somebody who really is a security specialist isn't you're a software developer and you get a better software developer, better. And then something apart here is learning security. It's not how it works. I've been at SBA Research for 11 years now. I've worked with many different software development teams, and there are always those engineers in those teams that are really good at security. If you have a closer look at who they are and how they approach the topic, is they're basically just good engineers. They're not seeing security as something separate. They just have a good and sound and robust understanding of their software, of their programming languages, of their runtimes, of their compilers, of their operating system that stuff is running on, of the container environment, everything. They just understand what is going on. And when you understand what's going on, you can assess the security, as we told before. So we, as a software security team at SBA Research, we have education programs for software developers. Sec4dev is one of those educational formats, but we also have, for some companies, we do something like a basic, advanced, and expert, where everybody who's involved in software development needs to learn the essentials about security development lifecycle. And then depending on what you do, for example, you're a web application developer, you can do the web app security training, or maybe you are an architect and you're not so much into coding, or you write some code, but most of the time you do architecture and design, then threat modeling training might make sense. or you're a DevOps engineer that deploys software in the cloud, then cloud security might make more sense. And then as an expert level, when we're in that field of software security for a longer time, you can maybe go towards a certification. There are two that we also do preparation courses for. One that is really related to software security is the CSSLP, Certified Secure Software Lifecycle Professional. That's really software, that's SDLC from left to right, a certification on that is really valuable. And then there's the big sister of the CSSLP, which is the CISSP, that is information security from left to right. Software security is only one out of, I think, 22 chapters in this course. So it's even broader than that. So that's what an education program can look like. It doesn't have to be like that, but that's a possibility. And it's really important to offer your engineers and software developers the possibility to learn about how to find, how to fix vulnerabilities, how to improve the process, what are the tools available, what are the upsides and downsides of each of those tools, because none of those is perfect. Even though some vendors might tell you, if you use our tool, everything is perfect, it's probably not the case. Requirements-driven testing is also one activity. So what we typically have in a requirements document is functional requirements. And they have been there forever and everybody knows they have to be there. But when it comes to functional requirements with security aspects, such as authentication or authorization, you don't find so much information usually in requirements documents. And then there are those pure security requirements, such as, DDoS protection. We might need that. And they usually don't really find their way into requirements documents. So make sure to cover those. What I have seen in the past is that companies try to go from 0 to 100. I've seen requirements documents where people copied a whole standard into the requirements document. Namely, I saw that a couple of years ago in a architecture review and a requirements review. They had the OWASP ASVS, the Application Security Verification Standard, that has design requirements in there. Pretty good document, by the way. They just copied the whole document into the requirements document. That was 30 pages of security requirements. Now, if those people who developed the software did an actual estimation on what it would have taken to implement each and every one of those things, it would have taken them 15 years to do that, as opposed to 1 year what it took in reality, right? So please don't do this. Don't just take ready-made lists and throw them into requirements documents. That's not going to work because 75% are not going to make a lot of sense in the target environment, or maybe it's not such sensitive information that we need all of those things really, right? Pick out the stuff that really is relevant to your environment. It's probably not a whole standard like ASVS. We told them not to do that and to pick out the stuff that's relevant. Threat assessment. Remember the bridge in the beginning. Now, if we compare the building and designing first and then building that bridge with the software development process, what those people did is they just quickly designed the bridge. Yeah, looks good. Let's go into implementation. That's what people also usually, unfortunately, do when they create software. Now, if they would have done a threat assessment before that, somebody might have noticed that it's not going to protect. It's not going to be solid when there are winds that are stronger than 60 kilometers per hour. And these are the things that you don't find when you do static analysis or dynamic analysis. That's things that you find when you do threat assessment. I have included in this presentation a short threat model that I created for typical threats that are posed to authentication. You can take this as an inspiration, or you can do your own. It really depends on the environment. But one thing is, for example, let's take the example of password guessing. So if you create an application that has a login, you might have the threat of password guessing. So someone might have a list of valid usernames, and they could try the top 100 passwords for each of those usernames. If a protection against this is missing in your application, this is not a bug. You won't find that line of code that is responsible for that problem. right? It's a design thing. It was not in a requirements document. It was not in the architecture and design. It was not in a threat model. So why should it be in the code? These are problems where you cannot find a single line of code or a single class that is responsible for this not being present. So if you only write functional requirements and then start coding, and we need a login is the only requirement, you're going to end up with a threat model that says password guessing is possible. This is not a bug. It's a flaw. A flaw is a threat that's related to design architecture requirements. It's not related to coding. And the bridge, it was not that screw that was missing that caused the bridge to collapse. It was the design of the whole thing that made it collapse. It was the design of the architecture system that made it collapse when somebody tried to guess passwords, and they actively guessed passwords and they got our admin account because there's no protection against password guessing. So in your head, try to make this, try to distinguish bugs from flaws. We are really good at finding bugs. We are not good at finding flaws yet, right? We're going that way, but we're not there yet. So a threat assessment is there to find those design flaws. For authentication systems, this could be one. Now we have, you see in this case, we have contradictory threats. If you have password guessing and you want to protect yourself against that, you're going to say, okay, let's lock out users after 5 unsuccessful attempts of authentication. When you do that, you open yourself up to another threat, which is account lockout. So people can go and systematically lock other people out. So if I lock you out after 5 login attempts, that's going to mean that I can take your username, just hit 6 wrong passwords, anything I type on a keyboard, and you're going to be locked out. So you see, you need to balance requirements. You need to balance the countermeasures against those threats. This is not an easy task, but I suggest that you sit down and have a look at the design, not at the code. Put the code away, only design documents and architecture components, their ways of communication, their technologies that they use, and have a look at what threats like these are posed to your system. There's the same guy like I showed you before, Sebastian de Leersnijder. He's working for a security consultancy, and he's the project lead for OWASP SAM. This company recently released the threat modeling playbook. I really have recommend you to have a look at it. You can find it at the OWASP threat modeling playbook. Just Google for that term, and you're going to find it online. You have a process that shows you how you can do threat modeling. There's another suggestion. Threat modeling also tends to have this air of mystery around it. People don't really know how it works. I'm sitting here, I have my architecture. How am I going to do threat modeling? Well, where do I start? I have pen and paper. What am I going to do? Right? This is always the question, and it's a good question because no one knows what exactly to do, and it's really hard to get started with this. Now, when Julien Veillon, he was the operations security guy at Mozilla before. Now he's working for Google in their cloud platform, and he developed an approach that's called rapid risk assessment. That's basically threat modeling in half an hour, and it's a really short process, and you can at least get the major threats out of your design. The talk is tomorrow, 2:15. It's in the afternoon because he's, I think, East Coast US and would have had to get up really early if it was earlier. So 2:15 tomorrow, Julien Veillon talking about a lightweight approach to threat modeling. Also a very important task when it comes to a software development process. There are different activities like architecture reviews, that's going to maybe penetration test, maybe some automated analysis of your code. There are threats or there are bugs or there are flaws that will come up when you do testing of your software. So it is important to have centralized tracking of those things and prioritization of things. So it is advisable to have maybe an issue tracker that has security flag. Make sure to create a label, security, and maybe also labels for severity so that you can distinguish that's critical, that's high, that's medium, just at least a rough severity rating for your flaws and for your bugs so that you can prioritize them well. So different sources of flaws and bugs that will emerge from different activities if you do them. Make sure to track them centrally. It's best to do it in just a normal issue tracker where you have all your other issues as well, and maybe give them a separate flag a separate label for security and for some severity levels. And ideally, they make the way to your source code in the form of a fix. Also, a very important part of a secure software development process is automation. So we want to have the OWASP SAM calls it a scalable baseline. So something sorts of tests that scale well. They don't find all sorts of bugs, but maybe at least specific sorts of bugs. And I want you to know which different tools are out there and what are their advantages and disadvantages. We're going to distinguish 4 of them. First one, static application security testing, SAST. 2 of our partners here are creators of SAST tools, so Micro Focus and NonType. They do SAST tools, for example. That's static application security testing on your source code. We're going to go into that in detail in just a moment. Dynamic application security testing means you're testing in a running application. So you have a running application, so a web application somewhere on a test or staging system, and you test there. That can be fully automated, although that's not really advisable. It can be a manual test process, or it can be something in between. And there's also a third category, interactive application security testing, which is, kind of in between. We're going to have a look. And I have a separate chapter on dependency checks because I think they are so important, because most of the code is third-party code, and we have to manage security of that third-party code as well. Okay, let's dive into static application security testing first. Static application security testing scans the source code. So there's no running application required. You just need your source code. Depending on the language, it needs to be compiled, if it's a compiled language. If it's a scripting language, it doesn't have to be compiled in a classical sense. But what the tools do internally is they build a so-called abstract syntax tree, or in short, AST. So that's basically it makes a model of all the ways through your code. So you can think of it like a tree where there's a statement where it starts, and you might have an if statement, you might have a loop here and there. So it builds a tree of all the ways of the execution flows that can go through the code, in very short. So the basic approach, sorry, I jumped over this, is input, way through your code, and sync. So you have an input. An input could be something like you read a parameter from an HTTP request. That parameter that is potentially tainted, that could stem from an attacker, or that could be manipulated. That parameter is put through your code by passing it over to functions and so on. And there's a sync somewhere at the end. And that sync is potentially vulnerable to some sort of vulnerability, say SQL injection. There's an SQL statement somewhere. So there's a source, HTTP request parameter, and there's a sync, a statement that reads something from your database. And there's a way through your code. So if there's no protection mechanism somewhere in the middle, you might be susceptible to that attack. So that's the basic approach that these SaaS tools do. The advantages, a very clear advantage, is that it gives you reproducible results, because it always works the same time. If you test the same software with the same version of the same tool, it's going to give you the same results. So it gives you reproducible and comparable results, right? It gives you good code coverage as well, because it scans all the parts of your code, which is, we'll see that, harder when you do dynamic analysis. The disadvantages is it only covers your code. So there might be dependencies and libraries and frameworks that you pull in during development, and those are usually not tested with a SaaS tool. So it gives you results for your own code. It can only detect a limited set of vulnerabilities, even though some vendors might tell you different. It's usually only very technical bugs that they can find. They cannot find flaws, right? They can find bugs. There's a specific problem or challenge when it comes to scanning microservices environments. On the left-hand side, we have a monolithic architecture. So all the code lives in a very, very big, huge code base. So the business logic is in there, data access, the user interface, it's all in one code base. Now, SaaS tools have a good time scanning this code, because the source, the way through the code, and the sync are all in the same code base. So the SaaS tool sees it all at the same time. So it can assess whether that piece of code is vulnerable or not. When it comes to microservices architectures, microservices means that I split up the functionality of this monolithic application to several smaller services that take input from other services. So if the user sends a request to the interface, it might go to this microservice first, then to the other one, and then back here, and then back here. Now, if I scan one single microservice with a SAST tool, that means that the source could be here. It could go through my microservice, and the sink could be somewhere here. So it lacks context. That's difficult, and it gives SAST tools a harder time finding vulnerabilities because source and sink are not in the same abstract syntax tree anymore. I have some sort of input here also, and I might have some sink by sending the request to another service, but it is harder to assess whether this is an actual vulnerability in that case or not because the SAST tool does not see the whole context. There's also a related talk at sec4dev that's tomorrow, 10:45. That's the second talk after Philippe Derek. And Artem Bychkov is going to talk about difficulties when integrating SAST tools into your pipeline. The QR code here gives you more information, or you can have a look at sec4dev.io/schedule. Now let's have a look at the second tool type, that is DAST, so Dynamic Application Security Testing. As I said in the beginning, you have a running application. You don't have just the source code, but you have a running test environment. Some tools have SAST elements built in as well, but that's not the primary focus. It's about testing the running application. The approach is not source, way through your code and sink. The approach is request response. So DAST tools send requests to your application, and depending on which response they get from your application, they might deem something vulnerable or not. So for example, if they search for reflected cross-site scripting, they're going to send a input with an HTTP parameter that contains a script tag, for example, and if that script code tag comes back in embedded into HTML without any encoding, it is vulnerable to reflected cross-site scripting. That's one classic example. So the approach is pretty different. I'm going to have a look at the advantages and disadvantages when we compare it to SAST. Now, interactive application security testing is basically like DAST. So we have a running application, but additionally, you have an agent running in the test environment application. And that makes DAST results more actionable because that agent that sits in your software on the server side that can basically observe each request as it comes in from the DAST tool and can tell more about the application structure and can maybe even tell you which line of code is affected when it finds a vulnerability. So it makes DAST results more actionable. It's a little harder to set up because you need to deploy that agent and keep it up to date on the server side. So back to DAST. Advantages, it touches more parts of your stack because a request might be going through not only your code, but also libraries, frameworks, runtime, containers, operating system. A request might go through even other microservices back there and then come back to the application. So the advantage is it goes deeper into your code. The disadvantage is that it doesn't go so broad into your code. Why is that the case? Now, imagine you have an application where you log in and you might have different roles. Say you have 5 different roles. There are end users that are not privileged. There's some users that can manage the recipes, and there are other users that can also manage users. Then there's an administrator, and then there's the system user that can do everything, even change configuration of the application. If you have those 5 roles and you're using a DAST tool that actively uses your application by sending requests, you have to make sure that the DAST tool knows all of those roles and logs in as all of those roles one after the other to see the whole attack surface. So if you don't give the tool the login credentials or ways to create a session, it's going to have only a partial view of your application. So testing the running application with a DAST tool goes deep into your stack, but it doesn't go as wide in your own code. Just as SAST tools, it can only detect a limited set of vulnerabilities. Some of you might be coding with single-page applications such as Angular, React, or Vue.js. DAS tools have a little bit of a hard time scanning those because they need a headless browser where they simulate browser activity. So that can be hard. Really have a look at the tool if it supports this, if you plan to implement DAS in your environment. It's hard to get good code coverage for the reason that I just said. So you have to have every role, you have to go through every multi-step form. You have to reach those, more shadowed parts of your application that are not used so frequently in order to get a big picture. Because if an attacker finds a vulnerability in there, it's enough. It doesn't have to be at the front door. Now, the hard part about dynamic tests, so dynamic application security testing, DAST, is to get so-called known good requests. What is a known good request? Imagine the following REST API. We have a profile picture GET request, so we can get the profile picture of the currently logged in user. And that user has a thumbnail picture in there. And say it has a width of 200 pixels. That's what I want. I want the thumbnail to be downsized to 200 pixels. I have hopefully some sort of input validation that this value up there is actually an integer. And I ask whether it's original or scaled. If it's original, so the width corresponds to the file that was initially uploaded, I just read it from the file system and give it back to the user. If it is scaled, I ask the scaling microservice if it can scale down the picture to this size and then give the picture back. Now, if the DAS tool does not know that this value has to be a number between 100 and 1,000, it's always going to be hitting the input validation, and you're not going to get any depth, right? You're never going to hit that scaling microservice back there if the tool does not know that this has to be a number. And this is, at a small scale, a problem that you will have at a big scale when testing bigger applications. You have to make sure that the testing tool has those known good requests very widely throughout your application. So SAST versus DAST. SAST has good custom code coverage and reproducible results. And DAST has good depth, but cannot get so good code coverage because you might miss those known good requests for edge functionality. Generally, tool weaknesses, those tools might know that injection is bad, but not that this user must not see this data set. So authorization problems can usually not be found with these tools. If you have an access control problem in your software, they're not going to find it because they don't know what to check against. They don't know if that HTTP request that goes to the server can be issued by a user that is not privileged, right? So access control problems are something that's really a weakness. Or think about password guessing. That's a flaw, not a bug. The SAST tool is not going to find if you can guess passwords or not. So design flaws cannot be detected. Be aware of this limitation. As you've seen already, if you do threat modeling, penetration testing, SAST, DAST, whatever it is, different tools will give you different results. Some might have a focus on flaws, other on bugs, certain bugs of this kind, certain bugs of the other kind. So make sure to use a variety of views on your software. A penetration test can be a good start to, let the professional have a look at the security of your software, and then from there start with implementing the first countermeasures. Automate, but do it bit by bit. Don't just mindlessly throw an expensive tool at it, because it's very tempting to take a lot of money, throw it at the vendor, and then say the vendor is responsible for showing me all the security problems. And even if they say they can find all of those, it's probably not the case. So be careful and do it bit by bit. Make sure it really serves your purpose. So these are some activities that I picked out of this OWASP SAM model. There's some security automation parts. There's some education guidance parts. There are some threat modeling parts. There's some vulnerability management parts, and so on. I suggest you to really have a look at this center because it gives you a broader view of what's going on. So what you get from it is a scored result for each function. So this is the result if you answer this the interview questionnaire. Don't let yourself be fooled by those numbers. It doesn't have to be, we don't have to reach 3 everywhere. Actually, it's not going to make sense in any environment. Make sure to get stronger in those environments where you think it gets you the most value for the effort you put into it. So every activity in there has the same weight. There's no maturity level 1, 2, 3. They all weigh the same. Every level has the same weight. And the score is not the ultimate goal. Focus on the roadmap and focus on the process that results from it. and take it to detect maybe blind spots in your environment. Don't take it as an absolute number and say, I want to reach 3 everywhere. That's not going to make sense in any environment, probably. Great. There's one activity that I want to have a closer look at. That's dependency management, because most of your code that's running in the production environment is not going to be your own code. So we don't have a direct influence on whether these people have done good work and they have created good code and readable, maintainable, secure code, reliable code. We just don't know. So we don't have a direct influence. But how can we still manage those dependencies and security as well as we can? What is a software component? It's something that you pull in as a library. For example, if you're a Java developer, you might use Maven and the POM XML file to pull in dependencies. If you are C#.NET, you might use NuGet. If you use Python, it might be PyP. If you use PHP, it might be Packagist Composer. If you use Ruby, it might be RubyGems. If you use NPM, and so on, right? Every major language has their package manager, and you can pull in dependencies from there. Now, the foreign code, such libraries and frameworks, usually make up for more than 50% of the running code. So most of the running code is not your own code. But we cannot go ahead and check every line of code we pull in. It's just not going to be possible. Maybe in some environments, we even have 95% foreign code. We're not going to have the time to check it all. But we can check for, and that's the major point here, for known vulnerabilities, because there are security researchers out there, like at SB Research, for example, or somewhere else, that check those libraries for known vulnerabilities. For this to work, I want to do this in an automated way. The dependencies must be declared machine readable. So declared in the file with their version. Don't just pull in char files and commit them to the repository, because this way a program cannot determine which version exactly you're using of that software. Okay, I showed that slide already very quickly, but I want to make a little guessing game here. So make sure to go into the chat. I have started an Angular project from zero. It just does hello world. So it does literally nothing. It shows a string. How many lines of code do you think of external dependencies I pulled into my node modules folder? So all the libraries that are part of a standard Angular project that are in the node modules folder, how many lines of code do you think that is? Make your guess in the stage chat, please. Angular is a single-page application framework for web frontends that has dependencies to external libraries. So if I start a new project, I pull in such libraries automatically. How many lines of code do you think I have in such a project? First guess is 5,000. 156 people in the session. Make sure to make your guess, not just one. 50,000, 10,000, 30,000, 120,000, 10,000, 42, over 9,000. Okay, there's one person that is somewhat close. Most of you are way, way off. Over 1 million, that gets it. It's about 3.2 million lines of code in the node modules folder to give you that application. 3.2 million lines of code. So not all of those are going to be ending up in the build application that is packaged in the end. That's for sure. But some of them will. So there's a potential of 3.2 million lines of code of vulnerabilities. That's a lot. So we need some way to manage these dependencies. Here's the CLOC command that you can use to count the lines of code in a software project. Yeah, so it's going to be, components are going to be libraries, frameworks, the runtime. It can be base images if you use Docker, for example. So the quality of those components, there's going to be a big variety of those. In order to lower the external dependencies that you have in containers, there's a talk by my colleague Reinhard Kugler. That's on Thursday, 2:15, and how to build a container without Docker or LXC, so just one processing container, so basically crafted by hand with no external dependencies. That's a way to reduce such external dependency checks. So what I suggest you to do is automate dependency checks and trigger them automatically every time you push something to the repository. And if you have known vulnerabilities in there above a certain threshold of severity, fail the build and force yourself to look after that and force yourself to update that dependency. If you don't push anything to that repository, make sure to even do that regularly in the background or to rebuild the container so that the dependencies stay up to date automatically, even though maybe you're not actively changing things in that repository. I've compiled a list of some dependency check tools. There's one by OWASP. It's called Dependency Check. I think Google engineers are working on a project. I can't remember the name. If somebody can remember the name, please post it in the chat. And there are some tools that are specific to some environments, such as, for example, retire.js for JavaScript or the npm audit command for npm JavaScript packages. There's the local PHP security checker for the PHP world. There's NuGet defense for .NET and so on. There are some commercial tools also that you can find down here, and some code repository software like GitLab and GitHub. They come with their own tools. Like GitLab acquired Gamnasium, I think 2 years ago, and they integrated this in their software, and now you can use it to check your dependencies. GitHub has something with Dependabot. It's their tool and how they call it. So depending on your environment, choose one of those tools. If you go towards automation, I would suggest that it's dependency checks first, because SAST and DAST and other things are harder to integrate. Dependency checks should really be the first thing you automate, also because it's most of your code. So choose your dependencies wisely. Don't just throw in dependencies just because they do something you need. Make sure to really need it and it's high quality. Have a declarative machine-readable list of dependencies. Don't just pull in stuff into your repository because it's harder to update. Check them automated, like with tools that I showed you before. Fail the build if there is a vulnerability, and rebuild and run those checks regularly, even if there's no push, because dependencies might get out of date and you might not be coding anything in that repository for a couple of weeks. Advanced, if you want to go the really advanced way, if you have good test coverage, you can have a bot. I think GitHub supports that. You can have a bot that submits pull requests with updates to your libraries automatically, and you can merge them if your tests are green. But that only works if you have a really good test coverage, and you can really rely on those tests to check if your software still works after the update. You can even merge it automatically so that updates happen automatically in the background. All right. So last or next to last chapter, and it's going to be short, common vulnerability classes. So we've talked about secure coding practices, how to protect against certain vulnerabilities, but which are the ones that we want to protect ourselves against? One very common list is the OWASP Top 10 that got renewed in 2017, and there are things in there that are common in web applications and that have a high severity. So a combination of those two factors makes those vulnerabilities be in this list. Some of them we have already talked about. We've talked about authentication threats. We've talked about injection a little bit. We've talked about cross-scripting a little bit. So make sure to understand what's in there. Make sure to understand what's behind it. There's a new list. I think it makes a lot of sense if you are API developer. So if you do a REST API, for example, and I've marked in bold the vulnerabilities that are basically new to this list, that are not in the classic OWASP Top 10. And it's those four. And I find especially interesting this one and this one. Excessive data exposure means you return more data from your REST API responses, such as, for example, you include password hashes in your profile responses. That happens really frequently in APIs. Mass assignment is the other way around. You can use, for example, an update request to your profile and change your role to admin in the same time by including an admin property. So these are two lists that are very helpful if you are a web application developer. There's also the SANS CWE Top 25 that includes also web application weaknesses, but also non-web application ones, so that some that are relevant for other environments. So these lists are really a good point to start understanding vulnerability classes. I tried to compile a list of the OWASP Top 10 combined with the OWASP API Security Top 10. And here I've tried to make a bit of a rating how well I can test for those vulnerabilities with SAST and DAST. And if you have a look at this list, how many of these are actually green, so can reliably be detected with SAST and DAST solutions, it's not so many, right? It's only a few of those. So that's why if a SAST or DAST vendor tells you we can cover the OWASP top 10, well, you probably cannot. Maybe you can cover specific aspects of each of those vulnerability classes, but even that is very optimistic. So be aware of that false sense of security that could emerge from using those tools, because that can be really dangerous. If you want more targeted protection than just throwing a tool at it and hope that everything is fine, I suggest you to do the following thing. Determine how important that application is in terms of sensitivity of the data that you process in there. Make sure to know what's your tech stack. So what is the libraries, frameworks, programming languages, and so on that you use for programming it. Determine relevant vulnerability types for each of those components, and then find out what can we do against each of them. There's a talk on YouTube about vendors versus the truth, and I try to give some perspective on the OWASP top 10 and the different dimensions that these vulnerability classes have. Some are distributed over the whole stack. Some are very focused on one line of code. Some can be easily detected with SAST and DAST. Others cannot. So I suggest you to find out for each of those vulnerabilities in the list, how technology that I use helps me already, what can still go wrong, how can I test for it, what can I do in terms of defense in depth, and what residual risk is left. And if you do that for important vulnerability classes, you can have a way more targeted protection. I'm gonna give you one example. It's already 12 o'clock. I'm gonna maybe 5 minutes over time at the end. I want to give you one example with Angular and cross-site scripting. So Angular is a front-end JavaScript framework for your web browser that you can use to code web applications where you have the presentation layer only in your browser. And they introduce a good separation of concerns. So you have the business logic and the data persistence on the server, and the browser does everything with regards to presentation. So if you go back one slide here and say, determine relevant vulnerability types for this component, in short, it's cross-site scripting. There isn't really anything else. I mean, there's things like regular expressions out of service, but that's a minor problem compared to cross-site scripting. So what are ways to screw up? It's by using bypass security trust. I suggest everyone who codes Angular search for this string in your code base and be aware of the problem that might arise from this. Or if I code completely, I bypass the framework completely and I use unsafe DOM APIs directly. So if you don't understand exactly what I mean by those things, no problem. I just have a list of things that could go wrong. So in a nutshell, cross-site scripting in Angular, if I have this as a user input that could end up in my web application as a cross-site scripting vector, or I have a link that has this, can also contain JavaScript. Angular, if I do this with in-array HTML, it sanitizes this because it's going to strip out all the parts of the code here that can contain JavaScript, which is awesome. I told you before that of the major single-page application frameworks, Angular is the best one in terms of security because it comes with a sanitizer. The same goes for the link. So it's going to put an unsafe colon in front of that string, and it's going to end up not susceptible to cross-site scripting. This is what I suggest you to create for each vulnerability, for each component. I have this vulnerability class of cross-site scripting. It can be a rather severe problem. Angular has a very good default protection, but when I have this in my code, I'm still susceptible to attack. I can use a SAST tool here to disallow the use of these unsecure functions, and I might be able to use a linter to disallow such bypasses of the framework to directly use the DOM. What are defense in depth measures that are available? Well, I could use a content security policy, and it works really well with Angular. What is a residual risk? I could still use insecure DOM APIs directly that are not in the list of this check, but that's a small residual risk. What are some links and references where I can read more about this topic here and there? So if you do this for each vulnerability class, you will have way more targeted protection, because if you look at this environment, at this framework, it has a very good default protection. And there are some edge cases, and I can specifically check for those edge cases with automation. That's it, basically. 3 minutes over time. I just have a list compiled with a few learning resources and where you can learn more about secure software development. So if you say, what is the one thing that I should do to be better at software security? Is cultivate a culture of continuous learning. We need to learn about how our programming languages work, how our frameworks work, how the browser works, how the security models of the browser work. Understanding all those things is key for securing our software. I can't just stay in my world of it needs to work in terms of function, and I leave security out and think about it later. It's not going to work in the long term. So simplification, reduction, and also developing by design countermeasures and doing some of those activities in the process, not just the secure coding part. So where can I learn about software security? By testing and securing your own software, that's the best thing you can do. And read up on those specific, take those top lists and take the first one and learn about it and try to apply it to your own software. This is the best way you can learn this. Of course, sec4dev is made for exactly that purpose. So we're a learning platform and also a platform for maybe security champions that do security in software of their organizations. And we have regular meetups. So here's the link to our meetup. Make sure to join. We are still in virtual mode. So meetups are virtual and everybody can be part of them. For web security, this is where, this is my main area of expertise. There's the OWASP Choose Shop, which is an awesome application that you can use to test your hacking skills. I really suggest you to take an offensive approach. So by hacking applications, Choose Shop is something that you can just spawn an instance online and you can try hacking the application. It is full of bugs and flaws that you can use to bypass security measures intentionally. There's also the Portspeaker Web Academy that you can use for free. You have to register, but then you can use labs online and spawn your own instances of small web applications that have specific vulnerabilities in them. Also, OWASP is a very good general resource. And specifically, I like OWASP SUM, of course, the one that I mentioned before, and the application security verification standard that has a list of security requirements that you can use to also take them and maybe realize them in your own software. Good. Wrap up. So what are the key takeaways, I think, from this introduction to software security? Most companies are software companies. Some realize it, others don't. The initial velocity that I get from creating a software, as fast as possible and then shooting it out to production goes to the cost of sustained velocity. So think about security and reliability from the start. It's going to save you money in the long run. So if you have to, have an argument with your CEO, tell them it's going to cost more money in the long run. Secure software can be created with any language, but knowing the security properties will help. Maybe choosing if you have 2 or 3 languages of your choosing for a specific project, or you can code in a few languages, maybe that one fits better in that case. Use OWASP SUM to widen your view on secure development. It's not just the coding part. It's not just the secure coding practices. It's also activities around it. But internalize those secure coding practices as a base. So they are a good baseline for producing good code. Clean code also tends to be testable and therefore more secure, because if people understand your code, they're going to find flaws and vulnerabilities in there. If they don't understand what's going on, creative thinking about it is basically impossible. If you want to go the steps towards automation, dependency checks are a very good first step towards automation, because they're good tools. They are already quite well integrated in platforms and tools. So dependency checks are a good first step. Then think about SAST and DAST for specific problems. But again, deep understanding of the software, of vulnerability classes, of threats is key to securing your software. Without understanding everything that's going on in there, it's hard to secure software. So make sure to educate yourself to gain knowledge about the environment, and you will be successful in securing your software. SPA Research, again, company I'm working for, we have services in that area in our software security team. We are, I think, 13 people right now. We do penetration testing. We also help people in threat modeling, in improving and checking the architecture of the software. We do security champion programs with companies to get somebody, the knowledge to take the responsibility of software security in their company. We also, take automation tools like SAST or DAST and help companies integrate it into their process. So if you need help in any of the things, we can help. By the way, you can win a 3D printer. That's what I wanted to tell you before we go into the questions and answers. So there's an expo section on the left-hand side. Don't click it yet because you're going to drop out of the session. But make sure that after the session, you visit the expo. And if you click on the I'm interested button, you're going to be in the list of people who can win a 3D printer. I think it's 20 kilos in weight or something. So make sure to go to the expo section and visit the Micro Focus stand. All right, 12:09, 9 minutes over. Open a new tab could help. Yeah, that's true. Questions. I have the Slido open on the other monitor. And I'm going to go, yes, it will be. Yet it is recorded and it will be available. So what are popular questions? I'm going to try to read them out and try to answer them live. The first question by Benjamin is, I like a simple description of separation of duties. Oh, I just got a coffee. That's awesome. Thank you. A simple description of separation of duties. Someone who uses a key to enter the house does not have the permission to create a new key. This is not separation of duties, because separation of duties would be, I have one thing I want to do, for example, open the door. If I needed two keys of two separate people to open that door, that would be separation of duties. What you mean is least privilege. So everybody has just the privileges that they need to do their day-to-day work, which relates to separation of duties. But separation of duties is one process, multiple people who have to unite and do it to open. So two keys necessary to open one door by two different people. That would be an example of separation of duties. I'm going to go to the next question by a person called Anonymous. Let's say I have a single page application and an API. Who is responsible for output encoding to prevent cross-scripting? The front end, the API, both. It is the single page application. It is not the API. Why? If you have an API like a REST API, that could be used by different clients. So the whole good thing about the separation of duties is that I have my single API, and I have maybe my web application with the single page application framework. I have a mobile app somewhere, and I have this fat client that also uses parts of the API. So it depends on the output context, what I need to encode how, because it might be HTML here, it might be native code here, and again, native code. So these two don't need to encode anything. So please do not encode data input and encode it in the database, because you will have to decode it when it comes out of the application. So if you have an API that speaks JSON, that returns JSON objects, you have to JSON encode so that you can break out of the JSON context on the server side. That's the responsibility of the backend. So it has to encode double quotes, but that's it. That's all of the responsibilities. So output encoding HTML and cross-scripting protection is definitely the responsibility of the front end, so of the single page application. Next question by Daniel. Any specific reason Python list of non-types of languages? We clarified that already. So Daniel is right on this one. It's a bit more difficult than what I put it on my slides. So I'm going to hop over to the next one. Would you say that pinning dependency versions is best practice? Pinning dependency versions. So what Mr. Anonymous or Mrs. Anonymous means by that is, if I have my list of dependencies and there's the name and the specific version of it on the side, should I write in there, I want major version 1, but I don't care about the current version? Or shall I write, I want version 1.2.5 and just exactly that version? I'm going to tell you, the answer isn't easy, because it depends on how the library does their versioning scheme. If they guarantee you backwards compatibility within a major version, which is a common practice in frameworks, for example, you can pin that major version. Take a look at, for example, PostgreSQL. They don't guarantee backwards compatibility, I think, within minor versions. So if from 10.2 to 10.3, the database data file scheme might change. So I would pin a minor version of it. It depends on the guarantees of backwards compatibility. If there are no guarantees by the library or it's not documented, I would opt for maybe having a more fine-grained pinning of your dependencies. Are the core design principles from safecode.org? I'm having a look at that moment. No, that's not the source, but I have put it on the slides. You will find in the slides there's a reference on the bottom of the slide there. Are the slides going to be shared after the sessions? Yes, they will, and the video is going to be shared on YouTube as well, so you can pass it on to your friends and colleagues. Okay, another question. Not sure if you can answer all of those. Is Markdown in R a similar example of cross-site scripting as in the mentioning of sanitization? Markdown is a special case because Markdown can possibly contain HTML. It really depends on the dialect that you're speaking in Markdown. If you have a variety that cannot contain HTML code, then you're safe from this. But requirement for sanitization, and the same one you do have when you use Markdown that can contain HTML that's interpreted as HTML. I'm not talking about code examples or something or code blocks in Markdown. I'm talking about formatting possibilities that can come in the form of HTML. So if you have that, yes, it is a case for sanitization. Absolutely true. All right. Done. Another question, anonymous. Is there something as I as a developer have to do for TLS, or is it just configuration operations, assuming I live in a non-DevOps world? It depends on your responsibilities, because in smaller companies, if it's DevOps people that do both things, it might be your responsibility, and if not, it's not. TLS, there are already many recommendations out there. There's, for example, the Mozilla Observatory that gives you TLS configurations ready for different web servers that are considered secure. So I suggest to take those resources for configuring your web server, and you can use, for example, the Qualys TLS check to check your public TLS server for its configuration. One very good piece of software that I love very much is the Caddy web server. So it's CADDY. It has an awesome TLS configuration by default. It's written in a memory safe language. It's written in Go, so no buffer overflows. And it has things like OCSP stapling by default. So that's an advanced TLS configuration. And what's good about it is it has built-in automatic TLS. So if you're a public web server that is exposed to the internet, it's going to pull a valid TLS certificate automatically from Let's Encrypt. You have to do nothing. The configuration needs to carry the name of the domain name of your web application, and that's it. If you have one line with just a domain name in it, it's going to pull a TLS certificate and have a really good TLS configuration. And that also works for local development. That's the coolest thing. It's a single binary web server. And if you hook it up locally on your machine, it's going to create the certification authority for your machine, put it into your trust store of your browser and operating system, and you have a local TLS trust established, and you can develop on TLS and test all those measures, which is awesome. It's Caddy web server, so if you worry about good TLS configurations, it's really hard to do in Apache and Nginx. With Caddy, it's really easy to do. There's a talk about the creator of Caddy also in the SBA Life Academy from last year, where he shows the web server and how it works. Yes, Nicolas Petri, my colleague, the one who just brought me the coffee, posted the link to the Caddy server in the chat. Another question by Daniel. How do session IDs relate to access or ID tokens, OAuth OIDC? Referring to your statement, the session is the only source of info for security decisions. So access or ID tokens. If you have, I'll take OIDC, OpenID Connect, as an example. So OpenID Connect is a protocol that you can use for federated identity. It means I have my application here. I don't want to implement authentication all by myself, but I want to have an external identity provider, such as I can use Active Directory, I can use Google for that purpose, I can use Keycloak, whatever it is, separate thing that specializes in authentication and identity. And in order to establish a trust between those two, I can use OpenID Connect. That means I log into my Active Directory or my Keycloak or whatever it is, and then it redirects me back to my application, and it carries an authorization token. And then my application can make a back channel request and get an ID token. ID token contains information about my identity, my name, my role, my email address. So how does this relate to session IDs? It should be unrelated, because when that authorization flow or authentication flow is done, and your backend application knows that I'm the user that I'm telling the application to be, I should establish an independent session. And that can be with just a random session ID, right? So don't reuse those ID tokens as session tokens, because they have a short expiry time, usually just a few minutes, because you need, for that moment where you get redirected, establishing the trust, and then you build an independent session with your application. So access or ID tokens are a bit of a different concept here. I hope that answers the question. If not, please submit another one. Hint for Thomas, Spreadshirt AT also available for the ladies. Okay, I'll have a look. When evaluates maturity according to SUM, does it make more sense to do it for teams, organizational structure, or applications, more than one team involved? I would start, if you're just getting started with OWASP SUM, I would start with one application. Why? Because it's usually easier to do than, bringing together lots of teams, convincing them that this is something that makes sense. Start with existing pockets of success, meaning you have a team that's interested in security, or you have a team that's interested in doing OWASP SUM assessments, that has heard about this talk or has seen Sebastian Schneider's talk about SUM and thinks it's something that makes sense and we should try out. If you have this team of people that has an intrinsic interest, start with them, show that it works, and then with that pocket of success, go to maybe your boss or say, okay, look, we have severely improved our process by just doing this and this and this. And we noticed that these are missing activities by taking OWASP SUM to broaden our view on secure application development or secure software development. And maybe I think it's better to convince people and start with a small pocket of success for this purpose. Yeah, I think that's it in terms of questions as far as I can see it. Make sure to follow me on Twitter if you liked that content and if you want to see more on that. It's _Thomas Conrad. I'll also be posting the links to the slides and video once these are ready. All right. So thank you, everybody, for being part of this session. I'm very pleased by the big interest in the topic of software security. I hope this, showing you the map gave you a good overview, and I can help you navigate through the world of software development and secure software development. Thanks, everybody, for watching. See ya.